Welcome to the Late Lab. It's a pleasure to have you here. Before settling in, it would be lovely to imagine where this finds you tonight. Perhaps somewhere quiet at the end of a long day, somewhere dimly lit and peaceful, somewhere the world has finally started to soften around the edges. Wherever you happen to be, hopefully it is comfortable, calm and just right for a slow wander through an intriguing idea. If these quieter explorations are the sort of thing you enjoy, subscribing and leaving a like does a great deal to help the channel continue growing. And to everyone already here, returning again and again to these late night journeys, thank you. The support is genuinely appreciated, and it helps keep this little corner of the internet gently humming along. Now, there is a slight risk with tonight's subject. It may not be the most sensible choice for anyone hoping to switch off completely, because once the universe starts behaving in ways that seem faintly unreasonable, it can be difficult not to pay attention. Still, there are worse reasons to stay awake a little longer than trying to understand why matter exists at all, and why the cosmos seems to have chosen something over nothing. So, let's ease into it. Why is there matter in the universe, and what created the strange cosmic imbalance that allowed everything we know to survive? Everything that can be touched, seen, measured, breathed, burned, frozen, built, broken, eaten, studied, or quietly stared at through a telescope is made of matter. Stars are matter, oceans are matter, skin, bone, breath, dust, salt, iron, calcium, carbon, clouds, and coffee are matter. Planets are matter, galaxies are matter. The page on a screen, the glow behind the screen, and the eyes looking at it are all matter too. It is so ordinary, so constant, and so thoroughly woven into daily life that it hardly seems strange at all. And yet, when physics looks at matter closely enough, its existence begins to feel less like a given and more like an unsolved problem. The difficulty is not that matter exists. The difficulty is that it exists in the amount it does, in a universe that appears to have given it no obvious right to survive. According to the best current understanding of the early universe, matter should not have emerged alone. In the intense heat and energy of the young cosmos, matter and antimatter should have been created together in nearly equal amounts. Antimatter is not science fiction, and it is not merely an idea invented to make particle physics sound more dramatic than it already is. It is real. For every matter particle, the equations of modern physics allow a corresponding antiparticle with the same mass but opposite electric charge and certain other reversed properties. An electron has a positively charged partner called a positron. A proton has an antiproton. Matter has a mirror population, waiting just across the conceptual room looking unhelpfully symmetrical, and that symmetry causes trouble. When a particle of matter meets its antimatter counterpart, they annihilate one another. Their mass is converted into energy, not bruised, not dented, not politely rearranged. Gone. The result is usually a burst of high-energy radiation, as if the universe briefly loses patience and turns solid existence back into light. This is not rare in principle. It is a standard feature of how particle interactions work. Matter and antimatter are both allowed. Matter and antimatter can both be created. Matter and antimatter can both be destroyed. There is nothing in the basic setup that seems to favour one over the other, strongly enough to fill galaxies with one and leave the other almost entirely absent. And yet here everything is. This is the central puzzle hidden inside ordinary existence. The observable universe is overwhelmingly made of matter, not a balanced mixture, not half and half, not a cosmic tug-of-war ending in a draw. Matter won, or at least matter remained, and antimatter did not remain in comparable abundance. Somewhere in the earlier stages of cosmic history, something introduced a tiny preference. Something tipped the balance, however slightly, and that tiny advantage was enough to shape everything that followed. The remarkable part is how small that advantage may have been. The universe did not need a dramatic bias. It did not need antimatter to be outnumbered by 1,000 to 1 or even by 10 to 1. Estimates suggest the difference may have been only about one extra matter particle for every billion matter and antimatter pairs. That is not a grand victory. That is barely a statistical nudge. It is the sort of margin that, in any ordinary setting, would seem too small to matter. Yet in the early universe, that minute excess changed everything. Almost all matter and antimatter annihilated each other, leaving behind an ocean of radiation and, crucially, a small residue of matter. That residue became stars, galaxies, planets, atmospheres, chemistry, oceans, cells, nervous systems, and the inconvenient habit humans have of asking why any of it exists. This is one of the reasons the question feels so oddly personal. It is not only about the cosmos in some distant, abstract way. It is about why there is enough surviving substance for bodies to form, for carbon chains to persist, for long-lived stars to shine, and for biology to begin. If the balance had gone the other way, or if there had been no imbalance at all, the familiar material universe would likely never have taken shape. There would be no rocky planets, no lingering clouds of gas condensing into stars, no periodic table at work in living tissue, and no sleepy species on one small world wondering what happened. The question of matter is also the question of continuity, structure, and survival. Modern physics has a great deal to say about the particles involved. The framework known as the Standard Model of Particle Physics describes the known, fundamental particles and the interactions among them with extraordinary accuracy. It was shaped through the work of physicists such as Steven Weinberg, Abdus Salam, and Sheldon Glashow, whose electroweak theory unified two of the fundamental forces, and it was refined and extended through contributions from many others, including theorists such as Howard Georgi and Helen Quinn. The Standard Model has been tested again and again in laboratories, especially in particle accelerators, and it performs impressively well. It predicts interactions, decay patterns, scattering outcomes, and particle properties with a level of precision that would make a watchmaker feel underqualified. But the Standard Model is not a complete account of why the universe looks the way it does. It describes how particles behave. It does not fully explain why matter survived in the amount required to build the visible cosmos. That distinction matters. A scientific theory can be powerful and still incomplete. It can describe the machinery without fully explaining the historical outcome. In this case, the machinery is exquisitely well understood in many respects, yet the final cosmic result still carries a faint smell of unfinished business. That is where the problem becomes especially interesting. The imbalance between matter and antimatter is not treated as a vague philosophical mystery, nor as a poetic shrug disguised as science. Physicists have identified specific kinds of mechanisms that could, in principle, produce such an asymmetry. These include ideas connected to baryogenesis, the generation of an excess of baryons such as protons and neutrons in the early universe, as well as possibilities involving neutrino physics, charge parity violation, grand unified theories, and forms of new physics that go beyond the Standard Model. The list is technical, certainly, but it is not random. Each proposal attempts to answer the same calm but stubborn question. How did a nearly symmetric beginning produce a visibly asymmetric universe? This is one of those rare scientific problems that operates on every scale at once. It belongs to particle physics because it involves the smallest ingredients of matter. It belongs to cosmology because it shaped the history of the entire universe. It belongs to astronomy because galaxies, stars, and planets depend on the outcome. It even touches chemistry and biology because the molecules of life can only assemble in a universe where matter remained available to do the assembling. The puzzle begins with tiny particles and ends with everything solid and structured that now exists. So the strange truth is that the ordinary world is not as ordinary as it looks. Matter feels familiar because it is everywhere. but its abundance may be the consequence of a very delicate irregularity in the early universe. Somewhere in that ancient furnace of radiation and particle creation, perfect balance failed by a hair. The failure was small, almost absurdly so, but the consequences were immense. The galaxies overhead, the ground beneath every footstep, the calcium in bone, the oxygen in blood, and the iron forged in long dead stars all trace back to that slight excess. Reality, on this point at least, may owe everything to a cosmic imbalance so small it almost sounds like a rounding error. And yet it was enough. Enough for matter to remain. Enough for structure to form. Enough for the universe to become not empty light, but a place filled with objects, landscapes, atmospheres, chemistry, memory, and time. Enough, in other words, for anything at all to be here. To understand why matter survived at all, it helps to look closely at what matter actually is. Not in the broad, everyday sense where matter means anything that takes up space and has mass, but in the more intimate physical sense, where familiar objects are stripped back layer by layer until only their smallest known ingredients remain. A chair, a mountain, a cup, a lung, a planet, and a star may appear to have little in common, but at a fundamental level they are all built from the same handful of components, arranged in different ways and held together by the same underlying rules. For a long time, atoms were thought to be the final pieces. The word itself comes from an ancient idea meaning something uncuttable, something beyond division. That confidence did not survive modern physics. By the late 19th century and the early 20th, experiments began showing that atoms were not solid little beads at all, but structures with internal parts. One of the crucial breakthroughs came from J.J. Thomson, working at the Cavendish Laboratory in Cambridge, who identified the electron in 1897. The electron turned out to be a small, negatively charged particle present in all atoms. This was a startling discovery, because it meant atoms were divisible after all, and nature had kept smaller machinery hidden inside them. The next great step came from Ernest Rutherford, whose gold foil experiment revealed that atoms are mostly empty space. That remains one of the more unsettling gifts physics has offered. Solid objects feel solid, yet the atoms inside them are mostly emptiness, with nearly all of their mass concentrated in a tiny central nucleus. Rutherford's work showed that the positive charge of the atom, along with most of its mass, sits in that nucleus, while electrons occupy the surrounding region. The atom was no longer a simple blob. It had become a miniature system with structure, proportion, and internal order. Then came James Chadwick, who discovered the neutron in 1932. This filled in another important part of the picture. The nucleus was not made of positively charged protons alone. It also contained neutral particles, the neutrons, which help stabilize atomic nuclei through the strong nuclear force. Protons and neutrons are similar in mass, far heavier than electrons, and together they form the dense core of ordinary atoms. Electrons shape chemistry, bonding, and electricity, while protons and neutrons provide most of the visible mass in everyday matter. So when looking at a hand, a stone, or a tree, most of the mass involved comes from the nucleus, not from the electrons dancing around it. For a time, protons, neutrons, and electrons seemed like a satisfying trio. Matter appeared to have been reduced to a manageable cast. Nature, of course, had other plans. As particle physics developed, protons and neutrons began to look less fundamental than they first seemed. Experiments involving high-energy collisions showed that these particles were themselves made of smaller constituents. This led to the quark model, developed independently by Murray Gell-Mann and George Zweig in the 1960s. In this model, protons and neutrons belong to a broader family called hadrons, and hadrons are built from quarks. A proton contains 2 up quarks and 1 down quark. A neutron contains 2 down quarks and 1 up quark. That may sound tidy enough, but the deeper reality is less like marbles in a pouch and more like a restless storm of interacting fields. Quarks are never found in isolation under ordinary conditions. They are confined inside larger particles by the strong nuclear force, one of the 4 fundamental forces of nature. This force is described by the theory called quantum chromodynamics, usually spoken of as the study of how quarks interact through particles known as gluons. The theory was developed in large part through work by David Gross, Frank Wilczek, and Hugh David Politzer, who helped explain a remarkable feature known as asymptotic freedom. Asymptotic freedom means that quarks behave almost like free particles when they are extremely close together at very high energies, but they become more tightly bound as they move farther apart. This is a wonderfully uncooperative feature of nature. Try to pull quarks apart and the force between them does not fade, gently away like gravity over distance. Instead, it strengthens. The result is that quarks remain confined inside protons, neutrons, and other hadrons. Nature, on this scale, behaves a little like a strict librarian who becomes more alert the moment anyone tries to leave with the books. Yoichiro Nambu also played an important role in shaping the modern picture, especially through ideas about spontaneous symmetry breaking, which became deeply influential in particle physics. The structure of matter is not just a list of particles. It is a system of symmetries, interactions, and broken symmetries, all woven together in a way that determines what kinds of particles can exist and how they behave. Matter is architecture, but it is living architecture, built from laws as much as from components. Within this architecture, protons and neutrons belong to a special category called baryons. That word matters because physicists assign them a quantity known as baryon number. A proton has a baryon number of 1. A neutron also has a baryon number of 1. Their corresponding antiparticles have a baryon number of -1. Particles such as electrons are not baryons and do not carry baryon number in the same way. This may sound like the sort of bookkeeping only a theorist could love, but it turns out to be essential. Baryon number helps track the presence of matter built from protons and neutrons, the very stuff that eventually forms atomic nuclei, stars, gas clouds, and living bodies. Under many ordinary circumstances, baryon number appears to be conserved. That means the total baryon number before and after an interaction stays the same. If that conservation were perfectly absolute under all possible conditions, then the cosmic imbalance between matter and antimatter would be extraordinarily difficult, perhaps impossible, to explain. A universe that begins with equal amounts of matter and antimatter would remain balanced if baryon number could never change. There would be no lawful route toward a surplus of protons and neutrons. No excess matter would remain after the great mutual annihilation of the early universe. And that is where the structure of matter begins to turn into a deeper mystery. The particles themselves are not enough. The forces are not enough. Even the standard model, powerful though it is, may not be enough if it cannot fully explain how baryon number might be violated under extreme conditions. This suggests that the visible architecture of matter could be part of a larger system whose deepest rules only reveal themselves at enormous energies, perhaps in the earliest moments after the Big Bang, or in physical regimes no laboratory has yet fully reached. So matter, when examined carefully, is neither simple nor static. It is layered. Atoms contain nuclei and electrons. Nuclei contain protons and neutrons. Protons and neutrons contain quarks. Quarks are governed by gluons and the strong nuclear force within quantum chromodynamics, and wrapped through all of this is the quiet arithmetic of conserved quantities such as baryon number, which may hold the key to understanding why anything substantial remains in the universe at all. What looks solid and familiar from a distance becomes increasingly strange up close. Yet that strangeness is not decoration. It is the reason the cosmos has shape, weight, chemistry, and duration. Matter is not merely what things are made of. It is the surviving residue of a very particular set of physical laws, delicately balanced and perhaps, at the deepest level, not quite as conservative as they first appear. If ordinary matter is the familiar furniture of the universe, antimatter is its unsettling reflection. It is not fantasy matter, not magical matter, and not a separate substance drifting in some hidden parallel realm. It is made from particles that correspond directly to the particles of ordinary matter, with the same mass but opposite values for certain quantum properties, especially electric charge. An electron carries negative charge. Its antimatter partner, the positron, carries positive charge. A proton is positively charged. An antiproton is negatively charged. The resemblance is close enough to feel almost tidy, and the consequences are violent enough to make tidy seem like the wrong word. Antimatter matters because it reveals just how symmetrical the laws of physics can appear at first glance. If nature allows one kind of particle, it may also allow a matching opposite. That idea now sits comfortably within particle physics, but when it first emerged, it was deeply surprising. It did not arise from someone peering through a telescope and spotting a glowing anti-moon. It came from mathematics, which is often how physics quietly announces that reality is stranger than expected. In 1928, Paul Dirac developed a new equation that combined quantum mechanics with special relativity. Quantum mechanics described the strange behaviour of matter on very small scales. Special relativity, developed by Albert Einstein, described how space and time behave at high speeds. Bringing the two together was not straightforward. Dirac's achievement was to write an equation for the electron that respected both frameworks. The equation worked beautifully, but it contained an uncomfortable feature. It seemed to allow solutions corresponding not only to the familiar electron, but also to a particle with the same mass and opposite charge. At first, that kind of result can look like a technical nuisance, the mathematical equivalent of finding an extra sock that does not belong to anyone in the house. But Dirac took the result seriously. He proposed that this opposite particle might be real. This was a remarkable act of confidence, because it meant trusting the structure of the theory enough to accept that nature might contain a particle no one had yet seen. In hindsight, that looks brilliant. At the time, it must have felt at least slightly unreasonable. A few years later, the universe reluctantly admitted that Dirac had been right. In 1932, Carl Anderson, working at the California Institute of Technology, was studying cosmic rays with a cloud chamber. Cosmic rays are high-energy particles arriving from space, and when they pass through the chamber they leave visible tracks. Anderson observed the path of a particle that behaved like an electron in mass but curved the wrong way in a magnetic field. That meant it carried positive charge. He had discovered the positron, the antimatter partner of the electron. Antimatter had moved from equation to experiment, from theoretical oddity to physical reality. This discovery mattered for more than one reason. It confirmed Dirac's prediction, which was a triumph for theoretical physics, but it also suggested that the particle world might be built on deep symmetries. Symmetry in physics does not merely mean visual neatness or pleasing geometry. It means that the laws governing physical processes remain unchanged under certain transformations. This is one of the most powerful ideas in science. Symmetry helps physicists identify what must remain constant, what kinds of interactions are allowed, and which features of reality are fundamental rather than accidental. Several forms of symmetry became especially important in particle physics. Charge symmetry asks what happens if a particle is replaced by its antiparticle, reversing electric charge and certain related quantum numbers. Parity symmetry asks what happens if spatial coordinates are flipped, like viewing the universe in a mirror. Time reversal symmetry asks what happens if the direction of time is reversed, so that processes run backward rather than forward. Each of these operations probes something deep about the structure of physical law. At first, physicists hoped that nature might respect them cleanly and universally. That hope did not survive intact. Parity symmetry, for example, turned out not to be conserved in weak interactions, a discovery associated with the work of Tsung-Dao Li, Chen-Ning Yang, and Qin-Shung Wu. Nature, on this front, turned out to have a preferred handedness. That was already a clue that the universe was less perfectly balanced than once believed. But there was still a more powerful combined symmetry waiting in the wings. When charge symmetry, parity symmetry, and time reversal symmetry are considered together, they form what is known as CPT symmetry. This combined transformation has a special status in modern physics. The CPT theorem, formalized through the work of physicists such as Gerhard Luders and Wolfgang Pauli, shows that any local relativistic quantum field theory satisfying certain broad assumptions should remain invariant under the combined operation of charge reversal, spatial inversion, and time reversal. That sounds forbidding, but the core idea is simple enough. If the theory is built in the standard way, then reversing charge, flipping space like a mirror, and reversing time all at once should leave the fundamental laws unchanged. This matters because it means antimatter is not some loose improvisation added for dramatic effect. It is woven into the deep structure of the theory. CPT symmetry strongly suggests that particles and antiparticles should have identical mass and closely linked properties, and so far, experiments support that expectation extremely well. Matter and antimatter, when viewed through the lens of this combined symmetry, appear to be bound by a deep and elegant rule. But elegance is not the same as perfect balance in every detail. Individual symmetries can fail even if the combined CPT symmetry remains intact. Charge symmetry can fail, parity symmetry can fail, and, crucially, the combined symmetry of charge and parity, known as CP symmetry, can also fail under certain conditions. That possibility becomes enormously important when trying to understand why matter survived, in greater abundance than antimatter. CP symmetry would imply that the laws of physics treat matter in a given process the same way they treat antimatter, in the mirror image of that process. If CP symmetry were exact and universal, then generating a lasting imbalance between matter and antimatter would be extremely difficult. The cosmos would remain too fair, too balanced, too committed to symmetry for any excess matter to slip through the cracks. But if CP symmetry is only approximate, if it can be violated in subtle ways, then the door opens. Matter and antimatter no longer need to behave as perfect opposites in every circumstance. A slight bias can emerge. That is the essential tension at the heart of antimatter. On the one hand, the particle world appears deeply symmetrical. Antimatter exists because the equations allow and in some sense require it. On the other hand, those same laws permit small asymmetries, tiny differences in behaviour that may become decisive under the extreme conditions of the early universe. It is as though the universe believes in symmetry as a principle, but not always as a strict policy. This is what makes antimatter so fascinating. It is not just a mirror, it is a test of how exact the mirror really is. Every positron, every antiproton, every carefully trapped antihydrogen atom studied in modern laboratories forces the same question into the open. If nature is so symmetrical, why is the visible universe not balanced between matter and antimatter now? Why is the mirror world real, mathematically grounded, experimentally confirmed, and yet so scarce in the cosmos around us? The answer, if there is one, does not seem to lie in the non-existence of antimatter. Antimatter is real. The deeper issue is that reality appears to treat the two sides with a slight preference, not dramatic one, not enough to announce itself loudly, just enough to matter. And in a universe where nearly everything may depend on the smallest imbalance, just enough is more than enough. Once antimatter had been predicted and then glimpsed in cosmic ray experiments, the question shifted from whether it existed to whether it could be made, handled and studied under controlled conditions. That was an entirely different challenge. Finding a positron arriving from space was one thing. Producing heavier forms of antimatter on demand inside a laboratory was quite another. Nature had revealed that antimatter was real. Physics now wanted to know whether it could be summoned deliberately, like a very expensive and somewhat temperamental guest. That effort depended on the rise of particle accelerators. These machines were built to give charged particles enormous energies and then send them crashing into targets or into one another. In doing so, they recreated conditions intense enough for new particles to appear. The principle behind this is simple in outline, even if the engineering is not. When enough energy is concentrated into a collision, that energy can be converted into mass, allowing new particles to be created. In other words, if the laboratory could not find enough antimatter lying around naturally, it could make some by spending energy rather aggressively. One of the great early successes came in 1955 at the University of California Radiation Laboratory in Berkeley, later known as Lawrence Berkeley National Laboratory. There, Emilio Segre and Owen Chamberlain led the experiment that discovered the antiproton. This was a major step forward. The positron had already shown that antimatter existed for electrons, but the proton is a much heavier and more structurally important particle. It sits in the nucleus of every hydrogen atom and by extension in the nuclei of all heavier elements. Confirming the existence of the antiproton meant that antimatter was not limited to one peculiar little particle. It extended into the deeper architecture of ordinary matter. The antiproton has the same mass as a proton, but the opposite electric charge. That might sound almost disappointingly neat, but neatness in physics often hides profound consequences. When proton and antiproton meet, they annihilate, converting their mass into other particles and radiation. The existence of the antiproton strengthened the idea that the particle world really does come in mirrored pairs, at least to a remarkable degree. The mirror was not decorative. It was built into the structure of the laws themselves. Soon after, antineutrons were also identified. These are the antimatter counterparts of neutrons, carrying the same mass but opposite values for certain internal quantum properties. Since neutrons carry no electric charge, they are slightly less theatrical than antiprotons, but no less important. Their discovery helped complete the picture that the building blocks of nuclei all had antimatter partners. By the middle of the 20th century, antimatter had become an experimental reality, not just an elegant, mathematical consequence. Particle accelerators continued improving over the decades, growing larger, more precise, and far more capable. They allowed scientists to produce a wide variety of antiparticles under controlled conditions. But producing them was only part of the challenge. Antimatter is famously difficult to keep around because the universe is annoyingly full of matter. A single antiparticle brought into contact with an ordinary surface does not sit patiently waiting for observation. It annihilates. This means antimatter cannot simply be dropped into a metal container and placed on a shelf beside the biscuits. It must be isolated using electromagnetic fields, high vacuum conditions, and very careful experimental design. This is where the story becomes especially delicate. At CERN, the European Organisation for Nuclear Research, scientists began producing and studying anti-atoms, most notably antihydrogen. Ordinary hydrogen consists of one proton and one electron. Antihydrogen consists of one antiproton and one positron. In principle, it should behave like a mirror image of hydrogen. In practice, creating and trapping it is an extraordinary technical achievement, because both ingredients must be made, cooled, combined, and held without touching ordinary matter. Two important collaborations in this effort have been Alpha and A-Trap. These teams developed methods for trapping antihydrogen atoms long enough to study them in detail. That may sound modest, but in antimatter research, keeping anything around for more than a fleeting instant counts as a triumph. The Alpha collaboration, associated closely with physicist Jeffrey Hangst, has been especially important in measuring the properties of antihydrogen and comparing them with those of ordinary hydrogen. These comparisons matter because hydrogen is one of the best understood systems in all of physics. Its spectral lines, energy levels, and transitions have been studied with immense precision. If antihydrogen were found to differ from hydrogen in ways not allowed by current theory, that would be deeply significant. So far, the news for lovers of symmetry has been reassuring, or perhaps mildly frustrating, depending on personal taste. Antihydrogen appears, within present measurements, to behave very much like hydrogen. Its spectral properties line up with what the fundamental theories predict. That supports the idea that matter and antimatter are governed by the same deep rules, at least in these respects. Still, the measurements continue because precision is everything here. A tiny discrepancy could hint at new physics, and tiny discrepancies are exactly what this entire cosmic mystery seems to enjoy. One of the most intriguing questions concerns gravity. Does antimatter fall downward in Earth's gravitational field in exactly the same way as ordinary matter? According to general relativity and the current standard assumptions of particle physics, antimatter should, respond to gravity just as matter does. But science is usually happier measuring than assuming, particularly when the question touches one of the most profound imbalances in the universe. That is why experiments involving anti-hydrogen and gravity have drawn so much attention. At CERN, researchers including Jeffrey Hangst and collaborators have worked on studies designed to observe how anti-hydrogen behaves under gravity when it is released from a magnetic trap. This is technically very demanding work because antimatter is difficult to make, difficult to cool, difficult to trap, and generally not inclined to cooperate for long. Even so, these measurements are crucial. If antimatter were to respond differently to gravity, even slightly, it would force a major rethink of modern physics. At present, the evidence indicates that antimatter falls downward, much like ordinary matter. That result supports current theory rather than overturning it. Still, even confirming expected behaviour has value. The more carefully matter and antimatter are compared, the clearer it becomes where symmetry holds and where subtle differences might still hide. And subtle differences are exactly what matter most in the story of the cosmic imbalance. This is why laboratory antimatter research is so important. It is not merely a technical demonstration or a scientific party trick involving very expensive particles. It is a way of testing the deepest assumptions about symmetry, forces, and physical law. Every antiproton produced in an accelerator, every antihydrogen atom trapped at CERN, and every measurement of antimatter motion under gravity helps narrow the range of possible explanations for why matter came to dominate the universe. The broader mystery remains unchanged, but the laboratory brings it into sharper focus. If matter and antimatter are nearly exact mirrors, then the imbalance must have arisen through some very specific process in the early cosmos. If a hidden asymmetry exists in the behaviour of fundamental forces, then experiments like these may one day help expose it. Either way, the work matters. The controlled creation of antimatter has turned an abstract cosmological puzzle into an experimental science. And that is one of physics at its best, taking something that sounds almost impossibly remote and coaxing it very carefully into a trap. When matter meets antimatter, the meeting is brief. There is no gradual blending, no stable compromise, no quiet coexistence. A particle and its antiparticle do not simply bounce off one another and go their separate ways. Under the right conditions, they annihilate. Their mass is converted into energy, and what had briefly existed as matter is returned to radiation. It is one of the cleanest and most dramatic transformations in physics, though dramatic in a very small and very untheatrical way. The universe does not gasp when it happens. It simply balances its books. This process follows one of the most important principles in modern physics, namely that mass and energy are equivalent and can be converted into one another. In annihilation, the rest mass of the particle and antiparticle is not lost. It is transformed. For an electron and a positron, the usual result is the production of high-energy light in the form of gamma rays. These are not ordinary visible rays, of course. They are electromagnetic radiation of far higher energy than the light seen with human eyes. Visible light warms a wall or illuminates a window. Gamma rays arrive with far more punch. They're a reminder that even tiny particles can carry astonishing amounts of concentrated energy. An electron is very small, but when an electron and positron destroy one another, the energy released is exact, immediate, and measurable. The event is a perfect example of how deeply physical law links matter and radiation. Instead of thinking of particles as little solid beads and light as something entirely separate, modern physics treats both as parts of the same deeper framework. Matter can become radiation. Radiation can, under the right circumstances, become matter. The boundary is real, but it is not final. Nature is more flexible than everyday experience suggests. This helps explain why the matter and antimatter problem is so serious. If the early universe created matter and antimatter in equal amounts, and if those particles were free to meet, then annihilation should have happened on an enormous scale. Almost everything would have disappeared into radiation. The surviving universe would have contained very little ordinary matter, and certainly not enough to build stars, planets, oceans, or anything with opinions about particle physics. The existence of a material cosmos therefore implies that annihilation happened widely, but not quite completely. A small excess of matter must have remained after the great cancellations were done. Annihilation is not merely a theoretical idea or a process confined to distant, cosmic history. It is observed in laboratories and used in medicine. One of the clearest real-world applications is positron emission tomography. In this technique, a radioactive substance placed inside the body emits positrons, the antimatter partners of electrons. These positrons travel only a short distance before encountering electrons in surrounding tissue. When they meet, annihilation occurs, producing gamma rays that move away in opposite directions. Detectors surrounding the patient register those gamma rays, allowing computers to reconstruct detailed images of metabolic activity inside the body. This is one of those quietly wonderful moments in science, where an idea that sounds almost absurdly abstract turns out to be useful in a hospital. Antimatter, which might seem suited only to deep space speculation and expensive accelerator halls, helps doctors study blood flow, detect cancers, and examine brain function. The universe, as it turns out, can be both mysterious and oddly practical. Even its most exotic features occasionally end up helping with very terrestrial concerns. Beyond medicine, annihilation can also be observed in astrophysical settings. Space is not completely free of antimatter. Positrons are produced in certain radioactive decays, in high-energy environments around compact objects, and in interactions involving cosmic rays. When these positrons encounter ordinary electrons, they annihilate and generate gamma-ray signatures that can be detected by instruments designed to observe the high-energy sky. Space-based observatories and gamma-ray telescopes have identified such emissions, including a well-known signal from the direction of the Milky Way's central regions. These observations show that antimatter does appear in nature and does undergo annihilation on astronomical scales. But the key point is what is not seen. If large regions of the universe contained abundant antimatter, especially on the scale of stars, galaxies, or clusters of galaxies, there should be vast boundaries where matter and antimatter meet. Along those frontiers, annihilation would produce enormous amounts of gamma radiation. This signal would be hard to miss. It would be a kind of cosmic warning flare, visible across great distances. Yet no such widespread glow is observed. Gamma-ray astronomy has found many energetic phenomena, but not the enormous annihilation signatures expected from a universe divided into large matter and antimatter domains. That absence matters. In science, not finding something can be as informative as finding it. The missing glow strongly suggests that antimatter is extremely rare on large cosmic scales. There do not appear to be nearby anti-galaxies drifting around minding their own mirrored business. The observable universe, as far as current evidence shows, is overwhelmingly made of matter. Antimatter can be produced in local processes and high-energy environments, but it does not exist in comparable abundance across the large-scale structure of the cosmos. This pushes the mystery further back in time. If the universe is not divided into separate regions of matter and antimatter now, then the imbalance must have been established before galaxies formed, before stars ignited, before atoms settled into stable arrangements. The difference must have emerged in the very early universe, when temperatures were immense, interactions were rapid, and the ingredients of reality were still being sorted out. The scarcity of cosmic antimatter is therefore not just an observational detail, it is a clue about timing. Whatever gave matter its slight advantage happened extremely early. That is what makes Annihilation so revealing. It is not merely destruction, it is evidence. Every time matter and antimatter cancel one another, the process confirms how perfectly matched they are in many respects. They carry equal mass, opposite charge, and a shared tendency to vanish into radiation when brought together. That symmetry is real, and because it is real, the surviving excess of matter becomes even harder to explain. The universe seems to have begun with ingredients that should have erased one another almost completely, yet somehow failed to finish the job. So Annihilation leaves behind more than gamma rays. It leaves behind a question. Why did the cancellation stop just short of totality? Why was there any residue at all? The stars overhead, the chemistry of the body, the carbon in living cells, and the stone beneath every footstep all suggest the same answer, though not yet the reason for it. Matter was granted the smallest of margins. Antimatter was not absent, not imaginary, not irrelevant, but outlasted by a fraction so tiny that it scarcely seems enough. And yet it was enough for everything. To understand why matter survived, it helps to return to a time before stars, before atoms, before light could travel freely across space, and before the universe had anything resembling structure. The Big Bang model describes the universe not as an explosion into empty space, but as the rapid expansion of space itself from an early state that was far hotter, denser, and more compressed than anything seen today. In those first moments, the universe was not filled with galaxies or glowing clouds. It was a dense, energetic sea of radiation and particles, with temperatures so extreme that ordinary language starts to sound a little underqualified. At such enormous energies, the distinction between matter and radiation becomes much less rigid than it appears in daily life. In the young universe, energy could be converted into particles, and particles could be converted back into energy almost immediately. Matter and antimatter were not rare or isolated. They were constantly being created in pairs, and just as constantly being destroyed again. Particle and antiparticle met, annihilated, and vanished into radiation. Radiation then produced new particle pairs. The whole environment was restless, fast and crowded, less like a calm cosmic beginning, and more like a furnace with no walls and no pause button. This constant creation and destruction happened because the early universe was in what physicists call thermal equilibrium. That phrase sounds rather peaceful, but in this context it describes a wildly energetic balance. Thermal equilibrium means that the different particles and forms of radiation interacting in the hot plasma were exchanging energy so rapidly and so frequently that their overall behaviour followed stable statistical rules. Nothing was still, but the chaos had order. The particle populations were being maintained by the surrounding temperature. As long as the universe remained hot enough, matter and antimatter could continue appearing and disappearing in near balance. That balance matters enormously. If the laws of physics treated matter and antimatter in exactly the same way, under all relevant conditions, and if the early universe began with equal amounts of both, then thermal equilibrium would preserve that symmetry for a time. Creation would produce both. Destruction would remove both. There would be no obvious reason for one side to gain a permanent advantage, yet the modern universe clearly contains such an advantage. That means something subtle must have happened while the universe was still very young, still hot, and still dense enough for these particle processes to dominate everything. The Big Bang model is supported by several major lines of evidence, and one of the most important is the expansion of the universe itself. Observations by Edwin Hubble and others show that distant galaxies are moving away, with more distant galaxies generally receding faster. This indicates that space is expanding. Run that expansion backward in time and the conclusion is difficult to avoid. The universe was once far smaller, denser, and hotter than it is now. That does not by itself reveal every detail of the earliest moments, but it provides the broad historical direction. The cosmos has been cooling as it expands, and the present calm grew out of a much more violent beginning. Another powerful piece of evidence arrived in 1965, when Arno Penzias and Robert Wilson discovered the cosmic microwave background radiation. They were working with a radio antenna at Bell Laboratories and found a persistent background signal that seemed to come from every direction in the sky. At first, it looked like an unwanted noise source. Famously, even pigeons became part of the story, which is perhaps reassuring. Even one of the most important discoveries in modern cosmology had to survive contact with ordinary bird-related inconveniences. What Penzias and Wilson had found was the cooled afterglow of the early universe, radiation released when the cosmos became cool enough for electrons and nuclei to combine into neutral atoms, allowing light to travel freely for the first time. This cosmic microwave background is one of the clearest confirmations that the universe really did pass through a hot, dense early phase. It is not merely background light, it is ancient evidence, stretched by cosmic expansion into the microwave part of the spectrum and now filling all of space. Its temperature today is only a few degrees above absolute zero, but it carries information about conditions in the early universe with remarkable fidelity. Later missions measured this ancient light in much greater detail. The Wilkinson Microwave Anisotropy Probe, often called WMAP, mapped tiny temperature variations across the sky and helped establish a precise picture of the universe's age, composition, and geometry. The Planck mission, operated by the European Space Agency, improved that picture further with even higher precision. These missions showed that the early universe was extremely uniform overall, but not perfectly uniform. There were tiny fluctuations in density and temperature, minute irregularities that would later grow into galaxies and clusters of galaxies under the pull of gravity. These observations also help constrain the amount of ordinary matter in the universe. Cosmologists can compare the cosmic microwave background, the abundance of light elements formed in the first minutes, and the large-scale distribution of galaxies to estimate how much baryonic matter exists. The answer is not arbitrary, it is measurable, and what is measured is a universe containing a definite excess of matter over antimatter, an excess small in origin but enormous in consequence. That point is worth lingering on. The matter density seen today does not require a huge early imbalance. It requires only a very slight one. Roughly speaking, for every billion matter and antimatter pairs in the early universe, there may have been just one extra matter particle. When the mutual annihilations ran their course as the universe cooled, the paired particles largely destroyed one another, leaving behind that tiny surplus. Everything familiar was built from that residue. The stars overhead, the heavy elements forged in stellar cores, the chemistry of planets, and the material of living bodies all depend on that minute symmetry. So the first moments of cosmic history were not only about heat and expansion, they were also about opportunity. In the early thermal bath, matter and antimatter were being produced and erased so rapidly that any small bias in the laws of physics could be magnified into a lasting difference. Once the universe expanded and cooled enough, the conditions of equilibrium began to fail. Particle reactions slowed. The cosmic furnace lost some of its ability to keep creating fresh pairs. Whatever imbalance had emerged by then would no longer be washed away so easily. That is why the earliest universe matters so much to this mystery. The present cosmos is too cool, too dilute, and too settled to explain the origin of the matter excess by itself. The explanation must lie in those first, brief intervals when energy was abundant, interactions were intense, and the difference between matter and radiation was still fluid. Somewhere in that early epoch, before atoms, before stars, and before the cosmic microwave background was released, the balance shifted, not by much, just enough for annihilation to leave something behind. enough for a material universe to persist after the fire cooled, enough for the sky, the ground, and every solid thing in between. Physics has long been guided by a quiet hope that nature, beneath all its complexity, is orderly in a very deep way. One expression of that hope is symmetry. In science, symmetry does not simply mean that something looks balanced or pleasing to the eye. It means that a physical process remains governed by the same laws even after a particular transformation is applied. If the rules stay the same when left and right are swapped, or when particles are exchanged for antiparticles, then a symmetry is present. These symmetries are not decorative. They help define what kinds of laws are possible in the first place. For a good while, symmetry seemed almost too reliable. Physicists found that many equations describing nature were remarkably elegant under transformations of space, time, and charge. This gave the impression that the universe might be at its foundations rather fair-minded. Reality could be violent, certainly, but perhaps not biased. Perhaps the deepest rules made no distinction between left and right, matter and antimatter, forward and backward, except in the most superficial senses. It was an attractive vision. As usual, nature accepted the compliment and then complicated it. One of the key symmetries in early particle physics was parity symmetry. Parity asks a simple question. If a physical process were viewed in a perfect mirror, would it still be allowed in exactly the same way? A mirror flips left and right. If parity is conserved, then the mirror version of a process should be just as natural as the original. At first, this seemed reasonable enough. Why should the universe care about handedness? Why should left and right matter to fundamental law? It would be a bit rude, frankly, if the cosmos had a preferred orientation built into it. For electromagnetic interactions and the strong nuclear force, parity symmetry appears to hold. But in the 1950s, doubts began to emerge about whether the weak nuclear force behaved the same way. The weak interaction is responsible for certain kinds of radioactive decay, including beta decay, and it had begun to look suspiciously unlike its more symmetrical cousins. Sungdao Li and Chenning Yang examined the evidence and pointed out that parity conservation in weak interactions had never actually been tested properly. It had largely been assumed. In physics, that can be dangerous. The universe has a habit of punishing assumptions with data. The decisive test came through the work of Qin-Shung Wu, an experimental physicist of extraordinary skill. In 1956 and 1957, Wu and her collaborators designed an experiment using cobalt-60 atoms, cooled to extremely low temperatures and placed in a magnetic field so that their nuclei were aligned. The idea was to observe the direction in which electrons were emitted during beta decay. If parity symmetry held, then the pattern of emission should look identical in the mirror version of the experiment. But it did not. The electrons showed a clear directional preference. The weak interaction was not indifferent to left and right. Nature, at least in this domain, had chosen a handedness. This was a profound shock. Parity violation meant that one of the most trusted assumptions in physics had failed. The mirror image of a weak interaction was not always physically equivalent to the original. The universe, deep down, was not perfectly symmetrical after all. It was not a total collapse of order, but it was a warning. Symmetry could be broken. Laws that looked beautifully balanced in one context could reveal a preference in another. Reality was subtler than expected, and perhaps a little less polite. Once parity had failed, physicists naturally looked for a rescue. Maybe the universe did not respect mirror symmetry alone, but perhaps it would respect combined transformation. If parity flips left and right, and charge conjugation swaps particles for antiparticles, then perhaps doing both together would restore the balance. This combined symmetry is called charge parity symmetry, or CP symmetry. In effect, it asks whether the mirror image of a matter process, with all particles replaced by their antiparticles, behaves the same way as the original. That seemed promising. Matter might prefer one-handedness, but antimatter in the mirror might compensate for it. the deeper fairness of the laws could still be preserved. For a time, that seemed to work. CP symmetry looked like a more durable principle. Cleaner foundation after parity alone had let everyone down, but the peace did not last. Later experiments showed that even CP symmetry is not exact. Certain subatomic particles, particularly neutral kaons, were found to behave in ways that slightly distinguish matter from antimatter even after mirror reversal is taken into account. The universe had, once again, kept the broad elegance but abandoned the absolute version of it. That discovery mattered enormously because it changed the question of cosmic imbalance from a philosophical curiosity into a plausible physical problem. If matter and antimatter obeyed exactly identical laws in all relevant processes, it would be very difficult to explain why the observable universe ended up dominated by matter. There would be no natural mechanism for one side to gain an advantage. But if symmetries can fail, even subtly, then the door opens. A tiny preference in the behaviour of matter over antimatter could, under the extreme conditions of the early universe, be amplified into a permanent cosmic asymmetry. This is the important shift. Symmetry violation is not just an oddity in particle experiments, it may be the reason anything material exists in the first place. The imbalance between matter and antimatter does not require a huge bias. It requires only a small one, operating at the right time under the right conditions. The early universe was full of high-energy interactions, constant particle creation, and constant annihilation. In such an environment, even a very slight asymmetry in the laws could leave behind a residue of matter after most matter and antimatter had cancelled each other out. So symmetry in physics is now understood in a more mature way. It remains central, it remains beautiful, it remains one of the most powerful guides to the structure of natural law. But it is not always exact in the naive sense. Some symmetries hold perfectly in known experiments, some hold only in combination with others, some are broken under particular interactions. And those breakings are not flaws in the theory. They are features of reality, clues about how the universe actually works. There is something strangely fitting about that. The material universe may exist because perfect balance was never quite perfect. The laws of physics seem to lean towards symmetry, but not toward absolute symmetry in every detail. The mirror is real, yet not flawless. Left and right are not always equivalent. Matter and antimatter are not always treated in exactly the same way, and in those slight failures, those tiny cracks in the apparent order, there may be enough room for stars, planets, chemistry, and living things to emerge. The cosmos, in other words, may owe its structure not to symmetry alone, but to symmetry with a small and decisive imperfection. Once it became clear that parity symmetry could fail, physicists were left with a smaller but still comforting hope. Perhaps nature did not treat left and right equally, but perhaps it still treated matter and antimatter fairly when the mirror was included as well. That combined idea, charge parity symmetry, suggested that if a process involving matter were reflected, and all particles were replaced by their antiparticles, the laws of physics would still behave in exactly the same way. It was a cleaner, deeper form of balance, and for a short while it seemed like it might survive where parity alone had not. Then the neutral kaon arrived to make life more interesting. Kaons are unstable particles containing quarks, and neutral kaons are especially useful because they can shift between different quantum states in a rather delicate and slightly mischievous way. They are produced as one type, evolve in time, and decay into other particles. Because of this behaviour, they became ideal systems for testing whether matter and antimatter truly obeyed the same rules under charge parity transformation. If CP symmetry held exactly, then certain decay patterns would be forbidden or would occur in perfectly balanced ways. The neutral kaon system turned out to be one of the rare places where that expectation could be tested with precision. In 1964, James Cronin and Val Fitch, working at Brookhaven National Laboratory along with collaborators James Christensen and René Turley, carried out the experiment that changed the subject forever. They studied long-lived neutral kaons and the way those particles decayed. According to the prevailing expectation, one particular decay into two pions should have been forbidden if CP symmetry were exact. Yet the experiment revealed that this decay did occur, rarely but unmistakably. The result was small, but it was real. CP symmetry, like parity before it, was not absolute. This was an astonishing result. It meant that matter and antimatter are not treated as perfect mirror partners in all weak interactions. Under certain conditions, particle decays can show a slight preference, a tiny skew in the rules. The universe had revealed another asymmetry, and this one was especially important because it touched directly on the problem of why matter survived. If matter and antimatter behave even slightly differently, then the early universe might have been able to turn that difference into a lasting imbalance. The key point is not that CP violation is large. It is not. It is subtle, almost annoyingly so, the kind of effect that refuses to shout. But in the early universe, subtle differences could matter enormously. When matter and antimatter were constantly being created and destroyed in the hot plasma of the young cosmos, even a tiny asymmetry in decay rates or reaction pathways could leave behind a minute excess of matter. That small surplus, preserved after most annihilations had run their course, could then seed the material universe that exists today. Still, discovering CP violation experimentally and explaining it theoretically were two different achievements. The 1964 results show that the symmetry failed, but it did not yet explain how that failure fit into the broader structure of particle physics. That explanation took shape in the early 1970s through the work of Makoto Kobayashi and Toshihide Maskawa. Building on earlier work by Nicola Cabibbo, they proposed a mechanism in which quarks could mix with one another during weak interactions in a way that naturally allowed CP violation. This idea required something bold. At the time, not all quark families had yet been confirmed experimentally, but Kobayashi and Maskawa found that CP violation could be accommodated mathematically if there were at least 3 generations of quarks. That was a striking theoretical insight. It implied the existence of additional quarks before the full particle family was established. Later discoveries of the charm, bottom, and top quarks helped confirm that this broader quark structure was real. The mathematical framework describing this mixing is known as the Cabibbo-Kobayashi-Maskawa matrix, usually called the CKM matrix. In simple terms, it describes how quarks can change flavor during weak interactions, shifting from one type to another with certain probabilities. These transitions are not random in the everyday sense. They follow a highly specific pattern encoded in the matrix, and the complex phase within that pattern allows CP violation to appear. That may sound abstract, but its meaning is concrete. The weak force does not treat all quark transitions with perfect symmetry, and that imperfection opens the possibility of matter and antimatter behaving slightly differently. Over time, this framework was tested in increasing detail. Important confirmations came from the Bell experiment in Japan and the Babar experiment at the SLEC National Accelerator Laboratory in California. These experiments studied particles called B mesons, which contain bottom quarks and are also excellent laboratories for observing CP violation. Both Bell and Babar found results consistent with the Kobayashi-Maskawa picture. The CKM mechanism was not merely a clever mathematical patch. It described something real in the behaviour of quarks and weak decays. This was a major triumph for the Standard Model. It showed that the theory could incorporate CP violation in a natural and experimentally testable way. It linked a strange asymmetry in kaon decays to the broader structure of quark families and weak interactions. It was elegant, predictive, and eventually strongly confirmed. In scientific terms, that is about as satisfying as things get. And yet, it was not enough. That is the frustrating beauty of this subject. The Standard Model does contain CP violation, and the CKM mechanism does explain the observed effects in kaons and B mesons remarkably well. but when physicists estimate how much matter excess this known source of CP violation could produce in the early universe, the answer falls far short of what is needed. The full observed cosmic matter surplus is vastly larger than the standard model seems able to generate on its own. The asymmetry exists, but it appears too weak, too modest, too polite to explain the full scale of the problem. So the discovery of CP violation did two things at once. It solved one mystery and deepened another. It proved that nature does allow matter and antimatter to behave differently. That was essential. But it also revealed that the known difference is probably insufficient. The door to explanation was opened, though only part way. The universe had admitted its bias, but not yet enough of it. That is why the 1964 experiment remained so central. Cronin and Fitch showed that the laws of physics are not perfectly symmetrical between matter and antimatter. Kobayashi and Maskawa showed how that asymmetry could arise within quark mixing. Bell and Bebar confirmed the mechanism in beautiful detail. And yet the cosmos still seems to demand more, somewhere perhaps in neutrino physics, perhaps in new particles, perhaps in forces not yet observed. There may be additional sources of asymmetry waiting to be found. For now, the lesson is clear enough. Matter was not favoured by a dramatic rebellion against symmetry. It seems to have been favoured by a slight, precise, and deeply buried imperfection in the laws of nature. That tiny imperfection may have made the difference between a universe filled only with radiation and a universe filled with galaxies, chemistry, and life. It was small in the equations, quiet in the laboratory, and immense in its consequences. By the late 1960s, the question had become sharper. It was no longer enough to say that matter had survived and antimatter had not. Physics needed to know what sort of process could actually produce that outcome. It needed a set of rules, not just a mystery. In 1967, Andrei Sakharov provided exactly that. He outlined the basic conditions that would be required for the universe to generate an excess of matter over antimatter. The proposal was brief, but it became one of the most important guides in modern cosmology and particle physics. It did not solve the problem by itself, but it told physicists what any successful solution would have to accomplish. The idea Sakharov was addressing is usually called baryogenesis. That word refers to the generation of an excess of baryons in the early universe. Baryons are particles such as protons and neutrons, the heavy ingredients that later form atomic nuclei and eventually most of the visible mass in stars, planets, and living tissue. If the early universe began in a nearly symmetric state, with matter and antimatter produced in almost equal amounts, then baryogenesis is the process that must have nudged the balance far enough for matter to remain after the annihilations had mostly finished. Sakarov argued that three ingredients were necessary. The first is baryon number violation. Baryon number is a quantity assigned to particles such as protons and neutrons. A proton carries baryon number 1. A neutron also carries baryon number 1. Their antiparticles carry negative 1. If baryon number were always and perfectly conserved in every process, then a universe that began with a net baryon number of 0 would remain at 0 forever. No lasting matter excess could ever appear. The accounting would never allow it. So if the cosmos ended up with more baryons and antibaryons, then somewhere, under some conditions, baryon number must have been allowed to change. This is one of those ideas that sounds almost administrative until its consequences become clear. Baryon number violation means the universe is permitted, at least under extreme circumstances, to alter the balance sheet. Protons and neutrons are no longer protected by an absolute cosmic bookkeeping rule. That possibility does not mean baryon number is casually violated in ordinary life. Tables do not dissolve because the universe has grown careless. But at very high energies, especially in the first moments after the Big Bang, the deeper laws may have been less conservative than the low-energy world now suggests. The second requirement is charge parity violation, usually spoken of as CP violation. This is necessary because even if baryon number can change, a perfectly symmetric universe would still tend to produce matter and antimatter in equal measure. CP symmetry would ensure that the relevant interactions treated baryons and antibaryons as mirror counterparts without any lasting preference. To generate a matter surplus, physical processes must distinguish at least slightly between the two. Matter and antimatter must not be handled with perfect fairness. There must be some bias, however tiny, in decay rates, reaction channels, or transition probabilities. This is where the earlier discoveries in kaons and later in bemesons become so important. They show that CP violation is real. Nature does allow such asymmetries. But Sakarov's insight was broader than any one experiment. He recognized that without some form of CP violation, the universe would be too balanced to produce the material excess now observed. Matter dominance requires not only that symmetry can fail, but that it fails in a way that gives matter a slight advantage under the right conditions. The third requirement is that these processes must occur out of thermal equilibrium. This condition is easy to underestimate, but it is essential. In thermal equilibrium, reactions and their reverse reactions occur in balance. The hot early universe was filled with exactly this sort of constant rapid interchange. Particles were created and destroyed so often that statistical balance was maintained. In such an environment, even if some asymmetry exists, equilibrium can wash it away. Forward processes and backward processes keep undoing each other. The universe, in effect, keeps resetting the game. To preserve a newly created matter excess, something must disturb that balance. The universe must pass through a period in which conditions change quickly enough that reactions can no longer maintain perfect equilibrium. Expansion helps with this. As space expands, temperature drops, reaction rates fall. Phase transitions may occur. Certain particles may decay after they have stopped being efficiently recreated. Under those circumstances, a small asymmetry can freeze in rather than being erased. Out of equilibrium, the cosmos becomes less forgiving. What happens once may not immediately be undone. That trio of conditions is elegant because it is both general and demanding. Baryon number must be violated. CP symmetry must be violated. And the relevant processes must happen out of thermal equilibrium. Remove any one of those, and the path to a matter-dominated universe becomes extremely difficult. Keep all three, and the problem becomes at least physically plausible. Later theorists spent decades exploring what kinds of models could satisfy Sakarov's conditions in realistic ways. Michael Dine became a major figure in work on baryogenesis, especially in connection with electroweak physics and with the Affleck-Dine mechanism developed with Ian Affleck. Alexander Kosenko contributed important ideas involving sterile neutrinos, leptogenesis, and non-standard cosmological scenarios that might generate asymmetry more effectively than the standard model alone. Mark Trodden helped refine the theoretical understanding of electroweak baryogenesis and the cosmological conditions needed for such mechanisms to work. These researchers, along with many others, took Sakarov's broad principles and tried to embed them in concrete particle theories and cosmological histories. That effort has led to a wide range of possibilities. Some models look to heavy particles that decayed in the early universe and produce slight asymmetries. Others rely on phase transitions in the electroweak era, when the Higgs field settled into its present form. Still others shift attention toward leptogenesis, where an asymmetry in leptons, especially neutrinos, is first generated and later converted into a baryon asymmetry through processes allowed in the early universe. The details differ, but all of these ideas are judged against the Sakarov conditions. They remain the test of seriousness. If a model cannot satisfy them, it cannot explain the cosmic imbalance. That is what makes Sakarov's proposal so enduring. It did not offer a single finished answer. It offered a framework that still organizes the search. It turned a huge and almost philosophical question into a more precise scientific one. Instead of asking vaguely why matter exists, physicists could ask which physical processes violate baryon number, which interactions provide enough CP violation, and which eras of cosmic expansion drive the universe out of equilibrium strongly enough to preserve the result. In that sense, Sakarov did something profoundly useful. He reduced a cosmic mystery to a set of conditions that real theories must meet. The universe still guards the full answer, but it no longer does so without constraints. Any successful explanation must pass through those three gates. Matter did not survive by magic, and it did not survive by accident alone. If the cosmos developed a preference, then that preference had to be written into the behaviour of particles, forces, and expansion in a very specific way. So the matter-filled universe now seen overhead and underfoot may trace back to three quiet requirements laid out in 1967: a broken conservation law, a broken symmetry, a broken equilibrium. Those failures, carefully timed and physically real, may have been enough to leave behind everything solid, structured, and alive. One of the most ambitious ideas in modern physics is that the strong nuclear force, the weak nuclear force, and the electromagnetic force may not truly be separate at the deepest level. They may only appear distinct because the universe is now cool and dilute by comparison with its earlier state. At extremely high energies, far beyond anything reached in ordinary experience, and still beyond the direct reach of current particle accelerators, these forces may merge into a single unified interaction. This is the central intuition behind grand unified theories, often called grand unification, and it is one of the boldest attempts to explain why the laws of nature look divided today while hinting at a simpler origin. The appeal of this idea is easy to understand. Physics has repeatedly found that apparently different phenomena can turn out to be aspects of a deeper whole. Electricity and magnetism were once separate subjects until James Clerk Maxwell showed that they belonged to the same electromagnetic framework. Much later, the weak nuclear force and the electromagnetic force were unified in the electroweak theory associated with Steven Weinberg, Abdus Salam, and Sheldon Glashow. That success encouraged a natural question. If two of the forces can merge at high energy, might the strong nuclear force join them as well, under still more extreme conditions? Several important early models explored exactly that possibility. Howard Georgi and Sheldon Glashow proposed one of the best-known grand unified frameworks in the 1970s. Around the same period, Jogesh Pati and Abdus Salam developed another influential model, one that treated quarks and leptons with a deeper structural relationship than the standard model ordinarily suggests. These ideas were not idle acts of mathematical extravagance, though particle theory does occasionally enjoy dressing extravagantly for dinner. They were serious attempts to describe a more fundamental symmetry that could exist only at energies vastly higher than those seen in modern laboratories. In grand unified models, the familiar distinctions between particle families can soften. Quarks and leptons may become members of a larger shared structure, and the forces that now appear separate may emerge from a single set of underlying fields. If that is true, then some conservation laws that seem strict in everyday physics may no longer be exact at those tremendous energies. This is where the idea becomes especially relevant to the matter problem. Grand unification can permit baryon number violation, one of the Sakarov conditions needed for baryogenesis. In many grand unified models, baryon number violation occurs through hypothetical heavy particles often called X-bosons, and in some models related Y-bosons as well. These particles would be unimaginably massive compared with ordinary protons or electrons, and would only have existed naturally in the very early universe, when temperatures and energies were correspondingly immense. Because they connect quarks and leptons in unusual ways, they allow processes that the standard model at low energies strongly suppresses or does not ordinarily permit. In effect, the cosmic bookkeeping becomes less strict. Matter can be reshuffled in ways that change baryon number, opening a route toward a net excess of baryons over antibaryons. This possibility is crucial. If X-bosons or similar grand unified particles were abundant in the earliest moments after the Big Bang, They could have decayed in ways that slightly favoured matter over antimatter, provided that the other Sakarov conditions were also satisfied. The key point is that grand unification offers a concrete setting in which baryon number violation is not an afterthought or a patch. It arises naturally from the deeper structure of the theory. That makes grand unified physics one of the most attractive frameworks for explaining how the cosmos might have acquired its slight material surplus. There is, however, a price for such ambition. Grand unification usually operates at energy scales so high that direct experimental confirmation is extremely difficult. Physicists cannot simply build a machine the size of a continent and switch it on after lunch. So instead, they search for indirect signatures. One of the most important of these is proton decay. In the standard model, the proton is effectively stable for all practical purposes. It does not appear to decay on timescales relevant to the age of stars, planets, or civilizations. But in many grand unified theories, the proton is not absolutely stable. It can decay through extremely rare processes mediated by those very heavy unified particles. A proton might transform into lighter particles, such as a positron and a neutral pion, though the exact channels depend on the specific model. The predicted lifetime is enormous, vastly longer than the age of the universe, which is why no one notices protons quietly disappearing from breakfast tables. Still, with enough matter observed for long enough, even incredibly rare decays might eventually be seen. This is why experiments such as Super Kamiokande in Japan are so important. Super Kamiokande is a huge underground detector filled with ultra-pure water and lined with sensitive light detectors. It was designed for several purposes, including the study of neutrinos, but it is also one of the world's leading instruments in the search for proton decay. By monitoring an enormous number of protons over long periods, it can look for the faint signatures that would indicate one has decayed. So far, no confirmed proton decay has been observed. That absence has already ruled out some of the simpler grand unified models, or forced their characteristic energy scales higher. Yet even a non-detection is useful. It narrows the theoretical landscape. It tells physicists which versions of grand unification remain plausible and which have become difficult to defend. If proton decay were ever observed, it would be one of the most important discoveries in the history of physics. It would show that baryon number is not exact, that protons are not eternally stable, and that some deeper unified framework likely governs matter at extreme energies. It would be a major clue not only about the forces of nature, but also about the origin of the cosmic matter excess. That connection to baryogenesis is what keeps grand unified ideas so compelling. The early universe was hot enough, at least in principle, to pass through regimes where unified symmetries could have been active. In such an environment, heavy particles like X-bosons could have been created and then decayed as the universe cooled. If those decays violated baryon number and contained enough asymmetry between matter and antimatter channels, they could have helped establish the tiny excess of matter that later survived annihilation. The visible universe might then be the cooled residue of a much deeper phase in which the familiar divisions among forces had not yet appeared. So grand unification remains one of the most elegant possibilities on the table. It offers a picture in which the forces are simpler at the beginning than they are now, where baryon number can be broken naturally, and where the earliest moments of cosmic history become the stage on which matter gained its slender advantage. Whether nature truly follows that script is still uncertain, but if the universe once lived under a more unified law, and if that law permitted just enough asymmetry to leave matter behind, then every atom in every star may owe its existence to physics written at energies almost beyond imagination. The Higgs field is one of the strangest ingredients in modern physics because it is both invisible and unavoidable. It does not look like a field in the everyday sense. There are no ripples on a surface and no glowing lines hanging in space. Yet according to the standard model, this field fills the entire universe, and fundamental particles interact with it constantly. That interaction helps determine whether a particle remains massless, like the photon, or acquires mass, like the W boson, the Z boson, and the quarks and leptons that make up ordinary matter. In that sense, the Higgs field is not just another feature of physics, it is part of the background structure that allows the material world to have weight, inertia, and stability. The basic idea is known as the Higgs mechanism. In the early universe, at extremely high temperatures, the electroweak force behaved as a more unified interaction. As the universe expanded and cooled, the Higgs field settled into a non-zero value throughout space. This changed the behaviour of certain particles. Instead of remaining massless, they began interacting with the field in a way that gave rise to mass terms in the theory. The process is often described with metaphors involving crowds, resistance, or movement through a medium, and some of those metaphors are serviceable, though a few are a little too pleased with themselves. The deeper point is that mass, in this part of physics, is not simply an intrinsic label attached to particles from the start. It emerges from the structure of the vacuum and the way particles couple to the Higgs field. This mechanism was proposed in the 1960s through related work by several physicists, including Peter Higgs, François Englert, Robert Brood, Gerald Guralnick, Carl Holgen, and Tom Kibble. Their collective achievement was to show how a gauge theory could produce massive force, carrying particles without destroying its mathematical consistency. That was essential for the electroweak theory to work. Without some version of this mechanism, the standard model would struggle to describe the weak interaction in the form that experiments actually observe. For decades, however, the Higgs field remained a theoretical necessity without direct confirmation. Physicists could see the need for it in the equations, but the particle associated with excitations of that field, the Higgs boson, had not yet been found. That changed in 2012 at CERN, the European Organisation for Nuclear Research, when the ATLAS and CMS experiments at the Large Hadron Collider announced the discovery of a new particle consistent with the Higgs boson. This was one of the major experimental achievements of modern physics. It confirmed that the field responsible for electroweak symmetry breaking was not just elegant theory. It had a real measurable signature in the universe. The Higgs boson itself is not the field as a whole, just as a ripple is not the entire ocean. It is an excitation of the field, a detectable quantum manifestation of something otherwise spread throughout all space. Its measured properties have so far aligned closely with the standard model, which is both reassuring and slightly inconvenient. Reassuring because the theory works, inconvenient because the matter-antimatter problem strongly suggests that the standard model is not the full story. So physicists naturally ask whether the Higgs sector, the part of the theory involving the Higgs field and its associated particles, might be richer than the simplest version suggests. That possibility has led to the study of extended Higgs sectors. Instead of a single Higgs field, nature might contain multiple Higgs fields or additional scalar particles. A scalar particle is one with no intrinsic spin direction, and the known Higgs boson is the first confirmed example of an elementary scalar particle. But there is no deep law insisting that it must be alone. Many theories beyond the standard model introduce extra Higgs bosons, charged Higgs particles, or additional neutral scalars and pseudoscalars. These richer frameworks can change the behaviour of the early universe in important ways. This is where the matter problem becomes especially interesting. In the standard model, the known sources of CP violation appear too weak to explain the observed cosmic matter excess. But an extended Higgs sector could provide stronger CP violating effects. Theorists such as Howard Haber and John Ellis have explored models in which additional Higgs particles alter the dynamics of electroweak interactions and introduce new asymmetries. These models do not guarantee a solution, but they make one more plausible. The Higgs sector, in other words, may not merely explain mass. It may also help explain why matter was favoured over antimatter. One of the central ideas here is electroweak baryogenesis. This is the proposal that the matter excess was generated during the electroweak phase transition, the period when the Higgs field settled into its present non-zero value, and the electroweak force split into the electromagnetic and weak forces seen today. If that transition was sufficiently abrupt, and if enough CP violation were present, then it might create the write-out of equilibrium conditions for baryogenesis. Particles interacting with the advancing boundaries of the new Higgs vacuum could behave slightly differently from their antiparticle counterparts, allowing a tiny excess of baryons to emerge. The appeal of electroweak baryogenesis is that it takes place at energies much lower than those associated with grand unification. That makes it, at least in principle, more accessible to experiment. The mechanism ties the cosmic matter asymmetry to physics that might leave traces in collider data, Higgs measurements, or searches for electric dipole moments. It is a more testable idea than some of the loftier models that require energies far beyond current reach, but it is also demanding. In the simplest standard model, the electroweak phase transition does not appear strong enough, and the available CP violation is too small. That is why extended Higgs sectors are so often brought into the discussion. They may provide the extra ingredients needed to make the mechanism work. This has motivated a great deal of experimental effort. At the Large Hadron Collider, physicists continue searching for new scalar particles beyond the known Higgs boson. They look for unusual decay channels, deviations in Higgs couplings, signs of charged Higgs states, and other hints that the scalar sector is more complicated than the standard model alone predicts. Precision measurements matter here just as much as dramatic discoveries. Even a small deviation from the expected behaviour of the Higgs boson could point toward new fields influencing the early universe. So the Higgs field sits at an intriguing crossroads. It already explains one of the most basic facts about the physical world, namely why many fundamental particles have mass. But it may also be tied to a much larger historical question. If the Higgs sector is richer than it first appears, then the same physics that shape the masses of particles may also have helped shape the survival of matter itself. The field that gives the universe weight may also have helped give it substance. That possibility remains unconfirmed, but it is far from fanciful. The early universe passed through the era when the Higgs field changed the structure of fundamental interactions. If any period was capable of turning a tiny asymmetry into a lasting material residue, that phase transition is a serious candidate. So the Higgs field is not merely a technical feature buried in the equations, it may be one of the central characters in the story of why there is anything solid here at all. Among the known particles of nature, neutrinos are some of the most elusive. They are electrically neutral, extremely light, and so weakly interacting that vast numbers pass through ordinary matter, almost as if it were not there. Every second, trillions of them move through the human body without leaving any noticeable trace. They stream from the sun, from radioactive decays inside Earth, from exploding stars, from the early universe, and from high-energy particle interactions throughout the cosmos. They are everywhere, and yet for a long time they seemed almost absent from practical physics, like quiet guests slipping through the walls and leaving before anyone could offer them a chair. Their ghostly reputation is well earned. Neutrinos interact through the weak nuclear force, and that force is much less influential over everyday distances than electromagnetism or gravity. Because neutrinos carry no electric charge, they do not respond to electromagnetic fields in the familiar way charged particles do. They also have extremely small masses, far smaller than those of electrons. All of this makes them difficult to detect. Huge detectors buried underground, placed under mountains, or sunk deep in mines, and water reservoirs are often needed just to catch a small number of interactions. The universe sends neutrinos in generous quantities. Physics receives them reluctantly. For many years, the standard model treated neutrinos as massless. That seemed acceptable because their masses, if they had any, were too small to measure easily, and the theory worked well enough, without giving them mass. But nature had other plans, as it tends to whenever physicists grow too comfortable. The crucial clue came from neutrino oscillations, one of the most important discoveries in modern particle physics. Neutrino oscillation means that a neutrino can change from one flavour to another as it travels. There are three known flavours: the electron neutrino, the muon neutrino, and the tau neutrino. If a neutrino is created as one flavour, it does not always remain that flavour. Over time and distance it can transform. That behaviour is only possible if neutrinos have mass, and if the flavour states are mixtures of different mass states. In other words, the identity of a neutrino is not fixed in the neat way once imagined. It is more fluid, more quantum mechanical, and rather less obedient than the simplest version of the standard model had assumed. Strong evidence for this came from experiments such as Super Kamiokande in Japan and the Sudbury Neutrino Observatory in Canada. Super Kamiokande studied neutrinos produced in Earth's atmosphere when cosmic rays strike the upper air. The detector found that the number of Muir neutrinos arriving from different directions did not match expectations, unless some of them were changing flavour during flight. The Sudbury Neutrino Observatory addressed the long-standing solar neutrino problem, in which experiments had detected fewer electron neutrinos from the Sun than solar models predicted. The solution turned out not to be that the Sun had made an embarrassing arithmetic error. Rather, some of those electron neutrinos were changing into other flavours before reaching Earth. Together, these experiments showed that neutrino oscillation is real. That result mattered enormously, because it implied that neutrinos possess mass. Not large mass, certainly, but non-zero mass. This was already enough to signal physics beyond the simplest standard model. It meant the theory was incomplete in a way directly relevant to the early universe. Whenever a particle thought to be negligible suddenly reveals hidden complexity, theorists tend to become very interested very quickly. Neutrinos became especially important in ideas about the origin of the matter excess through a theory called leptogenesis. This proposal, developed in influential form by Masataka Fukugita and Stomu Yanagida, suggests that the cosmic imbalance may have begun not with baryons directly, but with leptons. Leptons are the family of particles that includes electrons and neutrinos. In leptogenesis, a tiny asymmetry first appears between leptons and antileptons in the early universe. That asymmetry is then partially converted into a baryon asymmetry by known high-energy processes in the standard model called Sphaleron processes, which can reshuffle baryon and lepton numbers under extreme conditions. The elegance of leptogenesis is that it uses neutrinos, already known to be unusual, as the starting point for a much larger cosmic outcome. Instead of asking how protons came to outnumber antiprotons directly, the theory proposes that the first imbalance may have appeared in the lepton sector and only later fed into the baryon sector. Matter, in that picture, owes its survival to a quiet asymmetry among some of the least conspicuous particles in the universe. It would be a very neutrino sort of contribution. Subtle, nearly invisible, and somehow fundamental. A central ingredient in many versions of leptogenesis is the seesaw mechanism. This idea attempts to explain why the known neutrinos are so incredibly light. It proposes that alongside the familiar left-handed neutrinos, nature may also contain heavy right-handed neutrinos. These hypothetical particles would interact much more weakly and could have enormous masses compared with the ordinary neutrinos detected in experiments. The seesaw mechanism links the two scales together. The heavier the unseen right-handed neutrino states are, the lighter the familiar neutrinos can become. The result is a natural explanation for why neutrino masses are so tiny. Those heavy right-handed neutrinos would have been especially important in the early universe. If they existed, they could have been produced at very high temperatures and then decayed in ways that violated charge parity symmetry and generated a lepton asymmetry. That asymmetry could then be processed by the hot plasma into the baryon asymmetry now observed. In this picture, the visible material universe ultimately traces back to the decays of particles that no experiment has yet directly observed. It is a bold idea, but not an arbitrary one. It ties together neutrino mass, early universe cosmology, and the matter-antimatter problem in a single framework. Modern experiments are trying to sharpen this picture. DUNE, the Deep Underground Neutrino Experiment in the United States, is being designed to study neutrino oscillations with great precision, including the possibility of charge parity violation in the neutrino sector. Hyper-Kamiokande in Japan, the successor to Super-Kamiokande, will push these measurements further with a much larger detector and improved sensitivity. If neutrinos and antineutrinos are found to oscillate differently, that would be a major clue. It would not by itself prove leptogenesis, because the relevant early universe physics may involve much heavier particles than those seen today, but it would strengthen the case that the neutrino sector contains the kind of asymmetry needed to matter cosmologically. So neutrinos have moved from the margins of physics to somewhere much closer to the centre. Once treated as almost massless side characters, they are now deeply entangled with some of the largest questions in science. They reveal that the standard model is incomplete. They may hint at hidden heavy particles. They may carry forms of symmetry violation not yet fully measured, and they may hold the key to why matter survived at all. That is a remarkable turn for particles that barely interact, barely weigh anything, and spend most of their time passing through worlds unnoticed. The universe may have trusted some of its quietest ingredients with one of its loudest consequences. Antimatter is not only a laboratory curiosity. If it exists anywhere in large amounts beyond Earth, astronomy should have some chance of noticing. The universe is full of violent environments, high-energy particles, and radiation spanning the electromagnetic spectrum. If there were anti-stars, anti-clouds, or entire anti-galaxies drifting through space, their presence would not remain hidden forever. So astronomers have spent decades searching for signs of cosmic antimatter, not by looking for something that glows with a special anti-colour, but by tracking the physical signatures antimatter should leave behind in high-energy observations. One of the main methods is to search for antimatter in cosmic rays. Cosmic rays are fast-moving particles that travel through space and occasionally collide with detectors near Earth. Most of them are ordinary matter, such as protons or atomic nuclei. But antimatter particles can also appear in cosmic rays, especially positrons and antiprotons. These can be produced in ordinary high-energy collisions, for example when cosmic rays strike interstellar gas, or when energetic processes near compact astrophysical objects generate particle pairs. So finding positrons or antiprotons is interesting, but it does not automatically mean there are vast antimatter structures somewhere in the universe. Nature can make small amounts of antimatter through ordinary energetic events, without needing an anti-galaxy quietly floating nearby. That is why the real prize is heavier antimatter, especially anti-helium nuclei or anything even larger. A single antiproton can be made in many ways. An anti-helium nucleus is much harder to explain. Producing one through standard cosmic ray collisions is extremely unlikely. If anti-helium were detected convincingly in space, it could point to a much larger reservoir of antimatter, perhaps even antimatter stars or other structures where anti-elements are being formed naturally. In other words, it would be far more difficult to dismiss. One of the most important instruments in this search is the alpha magnetic spectrometer, mounted on the International Space Station. This detector was designed to study cosmic rays with exceptional precision, separating particles by charge, mass and energy. It acts rather like a customs officer for the high-energy universe, though with better hardware and fewer questions about liquids in hand luggage. By examining the trajectories of incoming particles in a magnetic field, the alpha magnetic spectrometer can distinguish matter from antimatter and look for rare components such as antiprotons, positrons, and potentially anti-helium nuclei. The instrument has gathered a vast amount of data on cosmic rays and has measured unexpected features in the flux of positrons and antiprotons. These results are scientifically valuable, though interpreting them is not always straightforward. Some excesses could be linked to astrophysical sources such as pulsars, which are rapidly rotating neutron stars with intense magnetic fields. Others have sparked speculation about dark matter annihilation, though that remains unsettled. What matters here is that the alpha magnetic spectrometer has not provided clear, universally accepted evidence for large-scale cosmic antimatter structures. The search remains open, but the universe has not yet handed over an anti-helium calling card with a forwarding address. Astronomers also search for antimatter indirectly by looking for annihilation signatures. If matter and antimatter come into contact, they annihilate and produce high-energy radiation, especially gamma rays. That makes gamma-ray astronomy one of the best ways to look for cosmic boundaries between matter and antimatter, regions. If there were entire antimatter galaxies mixed through the large-scale universe, then wherever ordinary matter drifted into them, or vice versa, enormous annihilation events should occur. Those events would generate gamma radiation on scales too large and too persistent to hide easily. This is where observatories such as the Fermi Gamma Ray Space Telescope become important. Fermi studies the sky in gamma rays, the most energetic form of electromagnetic radiation. It can detect emissions from pulsars, black hole jets, supernova remnants, and many other extreme phenomena. It can also monitor the gamma-ray sky for signatures consistent with matter-antimatter annihilation. Astronomers have indeed observed annihilation signals in some environments, particularly those involving positrons and electrons. There is a well-known gamma-ray signature associated with electron-positron annihilation in the region of the Milky Way center, but those signals reflect local production of antimatter in energetic astrophysical settings, not evidence for large antimatter galaxies. That distinction is crucial. Small-scale antimatter production is normal in a high-energy universe. Large-scale antimatter structure would leave a much more dramatic mark. If a galaxy made of antimatter existed near ordinary matter galaxies, the boundary zones between gas clouds, intergalactic medium, and in falling material would generate enormous gamma-ray emission. The same would be true on even larger scales if galaxy clusters contained mixed domains of matter and antimatter. Yet observations do not show this expected glow. The gamma-ray sky is lively, certainly, but it is not glowing in the way a mixed matter-antimatter cosmos should produce. This absence strongly suggests that large antimatter galaxies are unlikely, at least in the observable universe nearby, and on scales large enough for current astronomy to notice. It is always difficult to prove a universal negative with absolute confidence, because the universe is vast and not inclined to reveal every secret at once. Still, the evidence points in one direction. Antimatter exists in small amounts, created in local energetic processes and detected in cosmic rays. But there is no convincing sign that stars, galaxies, or clusters made predominantly of antimatter are common features of the cosmos. That conclusion matters because it narrows the timing of the cosmic imbalance. If the universe had separated into large matter and antimatter domains after structure formation began, traces of that separation should likely remain visible. There should be boundaries, collisions, and annihilation signatures on large scales. The fact that such evidence is lacking suggests the asymmetry was established much earlier, before galaxies formed, before stars lit up, and before ordinary matter began assembling into the structures now seen across the sky. In other words, the search for antimatter in the cosmos does not merely ask whether antimatter exists somewhere out there. It asks when the universe decided which side would dominate. The answer increasingly appears to be very early indeed. By the time the first large-scale structures emerged, the decision had already been made. Matter had already gained its tiny surplus, and antimatter had already been reduced to a rare and local phenomenon. So the sky tells a quiet but powerful story. Antimatter is real. It appears in cosmic rays. It is produced in energetic environments. It leaves measurable traces in gamma-ray observations, but it does not seem to build worlds on equal terms with matter. The stars overhead are, as far as present evidence suggests, made of the same kind of material as the ground beneath every footstep. The cosmic imbalance was not postponed until the age of galaxies. It was already written into the universe long before the first stars began to shine. Bariogenesis is the general name given to the set of processes that could have produced the small but decisive excess of baryons over antibaryons in the early universe. A baryon, in this context, means a particle such as a proton or neutron, the heavy matter that later formed atomic nuclei, and eventually the visible structures of the cosmos. The basic idea is simple enough to state. If the universe began in a nearly symmetric state, with matter and antimatter created in almost equal amounts, then some physical process must have shifted that balance very slightly in favour of matter before annihilation removed most of both. Baryogenesis is the attempt to explain how that shift happened in real physical terms rather than leaving it as a cosmic shrug. The challenge is that no single accepted mechanism has yet won the argument. Instead, physicists have developed a family of baryogenesis models, each trying to satisfy the Sakarov conditions in a realistic way. All of them must allow baryon number violation. All of them must contain some form of charge parity violation. All of them must operate out of thermal equilibrium at the right stage of cosmic history. Beyond that, the possibilities branch into several very different pictures of the early universe. One of the most discussed ideas is electroweak baryogenesis. This approach places the origin of the matter excess around the electroweak phase transition, the era when the Higgs field settled into its present non-zero value and the electroweak force separated into the weak nuclear force and electromagnetism. The attraction of this model is that it ties baryogenesis to physics that is, at least in principle, not absurdly far from experimental reach. It works with processes associated with the Higgs field, the weak force, and the hot plasma of the young universe, rather than relying only on vastly higher energy scales that may remain forever inaccessible. For electroweak baryogenesis to succeed, however, several demanding conditions must be met. The electroweak phase transition must be strongly first order, meaning it proceeds through expanding bubbles of the new vacuum rather than as a smooth gradual shift. Those bubble walls provide out of equilibrium conditions, because particles interacting with them behave differently depending on their direction and state. If enough charge parity violation is present, matter and antimatter can be treated slightly differently as they encounter these boundaries. That can allow a small baryon excess to develop outside or around the bubble walls before the transition completes. The difficulty is that in the simplest standard model, the Higgs boson mass and the known level of charge parity violation do not seem to support a strong enough effect, so electroweak baryogenesis generally points toward new physics, often in the Higgs sector or other extensions beyond the standard model. Another important model is Affleck-Dine baryogenesis, proposed by Ian Affleck and Michael Dine in the mid-1980s. This scenario arises in the context of supersymmetric theories, where the particle world contains additional scalar fields associated with ordinary matter fields. Scalar fields are especially useful in early universe cosmology because they can take on large values over space and evolve coherently as the universe expands. In Affleck-Dine baryogenesis, one or more of these scalar fields carries baryon or lepton number and develops a large displacement during the inflationary era or shortly afterward. As the field later evolves and begins to oscillate, it can generate a net baryon asymmetry. This idea is conceptually very different from electroweak baryogenesis. Rather than relying on subtle asymmetries at a later phase transition, Affleck-Dine baryogenesis uses the motion of a scalar field through its potential landscape to create a large net charge. One can think of the field as rolling and rotating in a way that stores an imbalance, which is later transferred to ordinary particles when the field decays. The mechanism has the appealing feature that it can generate a substantial asymmetry without needing the same delicate conditions as some other models. It also fits naturally into supersymmetric frameworks, where such scalar directions are often available. The trade-off, of course, is that supersymmetry itself remains unconfirmed experimentally, so the model is elegant but still speculative. Scalar fields more generally have become central to early universe thinking because of their role in cosmic inflation. Inflation is the idea that the universe underwent an early period of extremely rapid accelerated expansion, smoothing out large-scale irregularities and helping explain the observed uniformity of the cosmos. If scalar fields were active during or after inflation, they could have been displaced far from their present vacuum states. as they relaxed, decayed, or interacted with other fields, they might have produced substantial asymmetries in baryon number or lepton number. This makes the post-inflationary universe a fertile stage for baryogenesis. The same fields that shape the geometry and smoothness of the cosmos may also have influenced its material composition. Physicists such as Alexander Dolgov explored a variety of alternative baryogenesis scenarios, including models in which asymmetry could arise from non-standard cosmological dynamics, stochastic processes, or mechanisms involving unusual initial conditions and scalar field behaviour. Dolgov's work helped broaden the field by showing that baryogenesis need not be tied to a single narrow pathway. The early universe may have offered several opportunities for asymmetry generation, especially if new fields or interactions existed beyond the standard model. That broader perspective remains important, because current data constrain many simple models but do not yet isolate one definitive winner. Other models, including leptogenesis, also sit within this wider baryogenesis landscape. In leptogenesis, a lepton asymmetry is created first and later converted into a baryon asymmetry through high-energy standard model processes. Although the route is indirect, the goal is the same. Explain why matter outlasted antimatter. This variety of mechanisms reflects both the richness of theoretical physics and the stubbornness of the problem itself. The universe has left enough clues to guide theory, but not enough to remove ambiguity. That is why baryogenesis models are so closely tied to the search for physics beyond the standard model. The standard model is one of the most successful scientific frameworks ever built, but in its simplest form it appears unable to generate the observed matter excess in sufficient quantity. Its known charge parity violation is too small, and its electroweak phase transition is too gentle, so nearly every serious baryogenesis scenario asks for more. More fields, more symmetry breaking, more heavy particles, more hidden sectors, or more complicated early universe dynamics. None of. This means the standard model is wrong in the usual sense. It means it may be incomplete in precisely the way the cosmos most cares about. So baryogenesis is not a single theory, but a broader scientific program. It is an effort to identify the physical event, or chain of events, that tip the universe ever so slightly toward matter. Electroweak baryogenesis, Affleck-Dine baryogenesis, leptogenesis, and other models all represent attempts to tell that story with actual particles, actual fields, and actual cosmic conditions. Somewhere among those possibilities, or perhaps in a framework not yet fully imagined, lies the explanation for why annihilation was not the end of everything. The universe did not need a dramatic preference. It only needed a small, lawful, well-timed imbalance. Bariogenesis is the search for the moment when that imbalance became real. Supersymmetry is one of the most influential ideas in modern theoretical physics because it proposes that the known particle world is only half the cast. In its simplest form, supersymmetry says that every known particle has a heavier partner particle with a different spin relationship. Fermions, which make up matter, would be paired with bosonic partners. Bosons, which carry forces, would be paired with fermionic partners. Electrons would have selectrons. Quarks would have squarks. Gluons would have gluinos, and so on through the particle catalogue. It is an audacious idea, but not a whimsical one. It emerged from serious attempts to understand symmetry at a deeper level and to solve some stubborn problems left open by the standard model. The early formal development of supersymmetry is closely associated with Julius Wess and Bruno Zumino, whose work in the 1970s helped establish the first consistent supersymmetric quantum field theories. Later, theorists such as Nathan Seiberg made major contributions to understanding the rich mathematical structure of supersymmetric gauge theories, including how they behave at strong coupling and how different formulations may be related. These developments made supersymmetry far more than a speculative add-on. It became a robust framework in which physicists could explore deep questions about particles, fields, and unification. One reason supersymmetry attracted so much attention is that it addresses the Higgs mass problem, often called the hierarchy problem. In the Standard Model, the Higgs boson mass is sensitive to quantum corrections from very high-energy processes. Without some protective mechanism, those corrections tend to drive the Higgs mass to values far larger than the relatively modest scale actually observed. Supersymmetry can tame that problem because the contributions from ordinary particles and their superpartners can partially cancel one another. The cancellations are not magic. They arise from the symmetry relating fermions and bosons. In this way, supersymmetry helps stabilize the Higgs sector and makes the comparatively low Higgs mass seem less like an unexplained coincidence. That alone would make supersymmetry interesting, but the theory becomes even more appealing when the matter-antimatter problem enters the room. The Standard Model contains charge parity violation, but not enough to explain the observed baryon asymmetry of the universe. Supersymmetry offers additional possible sources of CP violation. The enlarged particle content, the extra couplings, and the more complicated scalar sector all provide new places where matter and antimatter interactions could differ. That matters because baryogenesis needs asymmetry in the laws, not merely in the final outcome. If superpartners or related supersymmetric fields were active in the early universe, they could have introduced the extra imbalance needed to tip the cosmic scales. This possibility is especially important in models of electroweak baryogenesis. In the simplest Standard Model, the electroweak phase transition does not appear strong enough, and the available CP violation is too small. Supersymmetric extensions, particularly versions with a richer Higgs sector and additional scalar particles, can improve both conditions. They may strengthen the electroweak phase transition and provide new CP violating effects near the expanding bubble walls of the new vacuum. Under those conditions, a small baryon asymmetry could be generated and preserved as the universe cooled. In other words, supersymmetry may not only make the Higgs mass less puzzling, it may also make the survival of matter more plausible. Supersymmetry also plays a role in other baryogenesis ideas, including Affleck-Dine baryogenesis. In that scenario, scalar fields associated with supersymmetric theories evolve in the early universe and generate a net baryon or lepton number. This works particularly well because supersymmetry naturally provides flat directions in field space, meaning combinations of fields that can be displaced to large values during or after inflation. As those fields later oscillate and decay, they can transfer their stored asymmetry into ordinary particles. That makes supersymmetry a remarkably versatile framework. It connects to Higgs physics, dark matter candidates, baryogenesis, and the deep structure of quantum field theory all at once. Ambitious certainly, but at least it is ambitious in an organized way. With all that theoretical appeal, it is natural to ask whether any supersymmetric particles have actually been found. So far the answer is no. The Large Hadron Collider at CERN has carried out extensive searches for superpartners, including squarks, gluinos, neutralinos, charginos, and other predicted states. These searches look for missing energy, unusual decay chains, and event patterns that would signal particles not included in the Standard Model. The results have been increasingly constraining. Many of the simplest and most elegant supersymmetric models have been pushed into more limited corners of parameter space, where the superpartners are heavier or the signals more difficult to isolate. That absence has not killed supersymmetry, but it has made the theory less carefree than it once appeared. It no longer enjoys the same easy optimism it had when many physicists expected superpartners to appear quickly at accessible energies. Still, more subtle versions remain viable. The supersymmetric spectrum may be heavier than originally hoped, more compressed, or arranged in ways that make detection difficult. The Large Hadron Collider has not closed the door entirely. It has simply made the search more demanding, and the theoretical storytelling less casual. Even that matters for the cosmic imbalance problem. If supersymmetry exists in some hidden, or more difficult form, then its effects in the early universe may still have been significant, even if its particles are hard to produce today. Early cosmology does not require superpartners to be convenient for modern collider schedules. It only requires them to have been relevant when temperatures were vastly higher. The early universe may have made use of physics now hidden behind energy scales not yet fully accessible, so supersymmetry remains a serious candidate in the broader search for hidden physics. It offers new particles, new interactions, new sources of CP violation, and new possibilities for baryogenesis. It helps address the stability of the Higgs mass, and provides fertile ground for early universe models in which matter gains its tiny but decisive edge over antimatter. Whether nature truly chose this path is still unknown, but if the material universe owes its existence to a deeper layer of symmetry, one that relates matter and force particles in ways only the hottest moments of cosmic history fully revealed, then supersymmetry would be one of the most profound ideas ever confirmed. Until then, it remains what it has long been: elegant, influential, elusive, and difficult to ignore. By now the essential fact is simple to state and extraordinary to accept. Matter did not survive because it overwhelmed antimatter in some dramatic cosmic victory. It survived because the balance was very slightly uneven from the start. For roughly every billion matter and antimatter pairs in the early universe, there may have been just one extra matter particle. That was all. Not a sweeping advantage, not a generous allowance, just a tiny surplus hiding inside a nearly perfect cancellation. Then, as the universe cooled and particle interactions changed, almost all the matter and antimatter annihilated one another, leaving behind radiation and that minute leftover residue. Everything solid now known appears to descend from that small remainder. It is hard to overstate how narrow that escape was. If the initial asymmetry had been zero, matter and antimatter would have cancelled almost completely, leaving a universe dominated by radiation. If the asymmetry had been much smaller, there might still have been too little matter to build the complex structures now filling space. The material universe was not guaranteed. It depended on a slight numerical preference written into the earliest physical processes, a preference so small that it sounds less like destiny and more like a rounding decision made by a very serious accountant. Once that surplus of matter remained, the universe continued expanding and cooling. In its earlier stages, it was still far too hot for stable atoms to exist. Electrons moved freely in a dense plasma, constantly scattered by radiation, while protons and nuclei remained separated from them. Light could not travel freely through this ionized environment, because photons were repeatedly scattered by charged particles. The universe, though already full of potential, was opaque. Matter existed, but it had not yet settled into the calm arrangements that would later support chemistry, stars, and planets. That changed during the era known as recombination, roughly 380,000 years after the Big Bang. By then, the temperature had fallen enough for electrons to combine with nuclei and form neutral atoms, mostly hydrogen and helium. The word recombination is slightly misleading because it sounds as though the universe was simply tidying up after itself. But the event was more consequential than the term suggests. Once neutral atoms formed, photons were no longer scattered so efficiently, and light could travel across space much more freely. The cosmic microwave background radiation dates from this period, carrying with it a snapshot of a universe that had finally become transparent. Recombination mattered because stable atoms are the foundation of the visible material cosmos. Without neutral hydrogen, there could be no long-lived gas clouds. Without those clouds, gravity would have had no ordinary matter to gather into stars, and without stars there would be no heavy elements forged in stellar cores, no rocky planets, no atmospheres, no water cycling over mineral surfaces, and no chemistry complex enough to lean toward biology. The tiny surviving matter excess did not merely remain, it began, slowly and quietly, to organize itself. gravity took over with patient persistence. The early universe was not perfectly smooth. Tiny fluctuations in density, preserved in the cosmic microwave background and later amplified by gravitational attraction, allowed slightly denser regions to pull in more matter. Over millions of years, these regions grew into clouds, halos, and the first gravitational wells in which gas could collect. The first stars likely formed a few 100 million years after the Big Bang. These stars were different from many of the stars seen today. They were born in a universe with almost no heavy elements, built largely from hydrogen and helium left over from the earliest cosmic stages. Their lives were intense and relatively short, and their deaths helped enrich the universe with heavier elements. From there, larger structures followed. Stars gathered into early galaxies. Galaxies assembled into groups and clusters. The cosmic web emerged, with filaments of matter stretching across immense distances and vast voids lying in between. None of this happened instantly, and none of it happened in isolation. Dark matter played a major role in shaping the large-scale gravitational framework, but ordinary baryonic matter was still the ingredient that cooled, condensed, formed stars, and built the visible world. The baryon asymmetry determined how much of that ordinary matter was available in the first place. If that asymmetry had not existed, or had been significantly smaller, the luminous universe would have been impoverished beyond recognition. Modern cosmological simulations help make this process vivid. Research groups at institutions such as the Max Planck Institute for Astrophysics have developed large numerical simulations to model the growth of cosmic structure from the early density fluctuations seen in the cosmic microwave background to the galaxy populations observed today. These simulations include gravity, gas dynamics, star formation, black hole feedback, and the exchange of energy and matter across vast scales. They show how delicate the universe's development really was. Cosmic structure is not a crude pile-up. It is the outcome of many physical processes acting together over billions of years, all dependent on the existence of enough surviving matter to participate in the first place. That dependency is easy to forget because matter now seems abundant. The night sky is full of stars. Galaxies number in the billions across the observable universe. Planets are common. Chemistry flourishes. But abundance at late times does not erase fragility at early times. The modern cosmos looks rich because a tiny asymmetry was amplified over immense spans of time. The original surplus was small. Gravity, cooling, fusion, and cosmic evolution did the rest. In that sense, everything familiar is an elaboration of a very slight initial difference. There is something quietly astonishing about that. A tiny failure of balance in the earliest universe made room for stable atoms. Stable atoms made room for gas clouds. Gas clouds made room for stars. Stars made room for carbon, oxygen, iron, calcium, phosphorus, and all the other elements that later entered rocks, oceans, atmospheres, cells, bones, and blood. A minute statistical excess became a cosmic inheritance. The material world was not simply given. It was rescued from near erasure by a preference so small that, at first glance, it seems almost too slight to matter. And yet, it mattered completely. The galaxies overhead, the silicate crust of planets, the chemistry of living cells, the deep oceans, the white bones of ancient animals, the iron in red blood, the calcium in teeth, the carbon in leaves and lungs, all depend on the survival of that early residue. The universe did not need a grand imbalance. It only needed enough matter to remain after annihilation had done almost all of its work. From that remnant came everything structured, luminous, and tangible. So the survival of matter was fragile, but not fleeting. It was precarious in origin and immense in consequence. The universe that followed was built from leftovers, though leftovers on a scale large enough to become stars and subtle enough to become thought. What remains most striking is not simply that matter survived, but that such a small difference was enough to turn an almost perfectly cancelling beginning into a cosmos filled with form, history, and life. The matter imbalance carries an unusual kind of weight because it sits at the meeting point of the very small and the very large. Particle physics deals with quarks, leptons, fields and symmetries, with the smallest known ingredients of nature and the rules that govern their behaviour. Cosmology deals with the evolution of the universe as a whole, with expansion, structure formation, and the history of everything visible. These two areas can seem very far apart in everyday thought. One sounds microscopic, the other impossibly vast. Yet the matter asymmetry binds them together with remarkable precision. A tiny difference in the behaviour of particles in the early universe appears to have shaped the existence of galaxies, stars, planets, chemistry, and life. That connection is one of the most profound features of modern science. It means the large-scale structure of the universe is not merely a matter of gravity acting on anonymous material. It depends on the prior existence of that material in the first place. The cosmic web, the galaxies hanging within it, the stellar nurseries, the planets circling ordinary stars, all of it rests on a prior question that is smaller, stranger, and more delicate. Why was there enough matter left over after the early annihilations for any of this to happen at all? Complexity in that sense is not just an accident of time and energy. It is built on a specific asymmetry written into the foundations of the cosmos. This is part of why the subject has a philosophical pull without needing to become vague or mystical. The imbalance is not merely a technical issue in particle theory. It touches the deeper question of why a structured universe exists instead of a far simpler one dominated by radiation. The visible cosmos was not guaranteed. It appears to have depended on a minute departure from perfect balance. That can feel unsettling, but in a useful way. It reminds us that reality is not obliged to match human intuitions about fairness, symmetry, or completeness. The universe may prefer elegant laws, but elegance does not always mean perfect cancellation. Physicists such as Frank Wilczek have often emphasized that symmetry is one of the deepest guiding ideas in fundamental physics, not because nature always displays symmetry in its final visible forms, but because broken, symmetry can be just as important as symmetry itself. A law may be elegant at a deep level while its outcomes are uneven, structured, and directional. Wilczek has written and spoken about how symmetry breaking gives the universe texture, variety, and the possibility of complexity. Without it, reality might remain far more uniform and far less interesting. Matter itself may be one more example of this pattern. The asymmetry between matter and antimatter could be a small break in balance that made larger forms of order possible. Leonard Susskind, from a somewhat different angle, has also explored how fundamental physics may hide deeper layers beneath the world that appears immediately visible. His work on quantum field theory, string theory, and the structure of the vacuum has helped shape the idea that what looks fixed and obvious at low energies may emerge from more subtle principles underneath. In that broader spirit, the matter asymmetry may not be a final fact in itself, but a symptom of deeper laws that remain only partly revealed. The imbalance may be telling us that something important is missing from the present picture, not because the current theories are failures, but because they seem incomplete precisely where the universe is most revealing. That possibility has led to an obvious but difficult question. Are there deeper principles or hidden symmetries still waiting to be discovered? It may be that the known forms of charge parity violation are only part of a larger story. It may be that the neutrino sector contains asymmetries not yet measured fully. It may be that additional scalar fields, heavy right-handed neutrinos, grand unified interactions, or supersymmetric particles once played roles that current experiments have not yet confirmed. The list of possibilities remains open because the data, while powerful, are not yet decisive enough to close the case. This uncertainty is not a weakness of science. It is one of its most useful conditions. Unresolved questions motivate new instruments, new searches, and new ways of testing old ideas. The matter asymmetry has helped drive experimental programs across multiple areas of physics. At colliders, researchers continue searching for new particles, hidden Higgs states, and departures from standard model predictions. In neutrino physics, experiments such as DUNE and Hypercameo-Candae aim to measure possible differences between neutrino and antineutrino behaviour with much greater precision. In underground detectors, proton decay searchers continue probing the possibility of grand unification. In precision experiments, physicists look for electric dipole moments and other tiny signs of new charge parity violation. The universe has not yet explained itself fully, but it has at least provided a useful to-do list. There is something quietly elegant about that. A question born in the first fractions of a second after the Big Bang now shapes laboratory work on Earth, deep underground, in giant water tanks, in accelerator tunnels, and aboard instruments in space. The imbalance is ancient, but its investigation is ongoing. In a very literal sense, the earliest moments of cosmic history continue to direct modern research. The past is not finished with physics, and physics is not finished with the past. What gives this puzzle its enduring force is that it seems too significant to be incidental. The matter excess is small, yes, but its consequences are enormous. That makes it feel less like a detail and more like a clue. It may be pointing toward undiscovered physics just beyond the edge of present understanding. Not necessarily something fantastical or dramatic, and perhaps not something that overturns everything known so far, but something real and missing. The imbalance may be one of the places where the universe is quietly telling us that the current map is accurate in many regions and incomplete at the border. So the philosophical weight of the matter asymmetry does not come from sentiment. It comes from scale, consequence, and incompleteness. A slight difference in the behaviour of fundamental particles may have made the structured universe possible. That difference is partly understood, but not fully explained. The known laws are powerful, but they do not yet close the circle. Somewhere between symmetry and its failure, between the early plasma and the galaxies now scattered through space, there remains an unanswered question. And because everything material seems to depend on that answer, it is not a small question hiding in a technical corner. It is one of the deepest clues the universe has left behind. The path to this mystery has been surprisingly orderly, even if the answer itself remains elusive. It began with the realization that the equations of physics were allowing more than anyone had expected. In 1928, Paul Dirac's work suggested that the electron might have a mirror counterpart with the same mass and opposite charge. That idea was not introduced as poetry or philosophy. It fell out of the mathematics. A few years later, Carl Anderson found the positron in cosmic ray experiments, and antimatter moved from theory into observation. The mirror world was real after all. From there, the picture deepened. Antiprotons, antineutrons, and eventually antihydrogen were produced and studied. Particle accelerators turned antimatter from a startling prediction into an experimental subject. The laws of physics seem to admit these mirror counterparts very naturally. Matter and antimatter appeared as paired possibilities built into the same framework, and that was exactly what made the larger problem more difficult. If nature allows both so readily, then why is the visible universe not balanced between them now? The answer could not simply be that antimatter never existed. It clearly did, and it still can be produced. Nor could the answer be that matter won by some enormous margin from the beginning. The evidence points instead to a tiny asymmetry, a minute preference that must have emerged under the extreme conditions of the early universe. That is where the subject shifted from particle catalogues to broken symmetries and cosmic history. The discovery of parity violation was one of the first major warnings that nature was not as perfectly balanced as it once seemed. Chien-Shiung Wu's experiment showed that the weak interaction distinguishes between left and right. Then, in 1964, James Cronin and Val Fitch, working with neutral kaons, showed that even charge parity symmetry could fail. Matter and antimatter were not treated as exact mirror partners in every weak decay. That result was pivotal. It revealed that the laws of physics contain a small but real asymmetry, and that asymmetry immediately became relevant to the existence of everything material. The theoretical framework grew sharper in 1967, when Andrei Sakharov identified the essential conditions needed to generate a baryon asymmetry. Baryon number must be violated, charge parity symmetry must be violated, and the relevant processes must occur out of thermal equilibrium. It was an elegant distillation of the problem. From that point onward, the question was no longer simply why matter exists, but what physical process in the early universe satisfied those conditions strongly enough to leave behind the tiny excess now seen in every star and planet. Later theorists pushed the search into several different directions. Some focused on quark mixing and the mechanism developed by Makoto Kobayashi and Toshihide Maskawa, which explained observed charge parity violation within the Standard Model. Others explored grand unified theories, where baryon number violation could occur naturally through very heavy particles. Still others investigated electroweak baryogenesis, leptogenesis, supersymmetry, and scalar field-driven ideas such as Affleck-Dine baryogenesis. Physicists including Michael Dine, Alexander Kusenko, Mark Trodden, Howard Haber, John Ellis, and many others expanded the landscape, trying to identify a realistic route by which the early universe could have shifted ever so slightly toward matter. And that is where things stand now. The known physics is powerful, but not yet sufficient. The Standard Model does contain charge parity violation, yet the amount appears too small to explain the observed cosmic matter surplus. The detected asymmetry is real, but it does not seem large enough. That is both encouraging and frustrating. Encouraging because nature has clearly shown that perfect balance is not the rule. Frustrating because the asymmetry needed for the universe still seems to exceed what the current framework can comfortably provide. That unresolved gap is what keeps the field moving. At CERN, experiments continue probing the Higgs sector, antimatter properties, and rare processes that might hint at new physics. At Fermilab, neutrino research and precision measurements help test possible sources of hidden asymmetry. At Keck in Japan, studies of flavor physics and particle decays continue the long effort to understand charge parity violation in greater detail. Around the world, detectors search for proton decay, electric dipole moments, unusual neutrino behavior, and rare transitions that would signal baryon number violation or new symmetry breaking effects. The universe has not yet revealed the decisive mechanism, but it has made the search precise enough to be scientific rather than speculative wandering. Future experiments may prove especially important. More sensitive neutrino facilities could reveal whether neutrinos and antineutrinos behave differently in ways that matter cosmologically. Improved collider measurements could uncover extrascalar particles or departures from Standard Model predictions. Underground detectors may continue tightening the limits on proton decay or perhaps, eventually, catch a glimpse of it. Precision studies of antimatter may confirm that its behavior matches matter in every measurable way, or uncover a deviation small enough to change the entire conversation. The possibilities remain open because the evidence is suggestive, not complete. That incompleteness is the heart of the mystery. The chain of discoveries has been extraordinary. Dirac predicted antimatter, Anderson found it. Cronin and Fitch showed that matter and antimatter are not treated identically. Sakarov identified the conditions needed for a cosmic imbalance. Later theorists proposed serious mechanisms for generating it. Experiments across decades have confirmed piece after piece of the story, and still, the final step has not been secured. The precise origin of the matter asymmetry remains unsolved. So the strange conclusion remains standing, quiet and stubborn. The universe appears to exist in its present material form because of an asymmetry that was almost vanishingly small, not a dramatic cosmic preference, not a grand act of creation tilted beyond doubt, but a slight imbalance in fundamental physics during the earliest moments of time. That tiny difference seems to have been enough for matter to survive annihilation, enough for atoms to form, enough for stars to ignite, and enough for galaxies, planets, oceans, cells, and minds to appear. The mystery remains because the universe has shown the result more clearly than the cause. Matter is here. The asymmetry was real. But the deeper origin of that asymmetry is still hidden somewhere between the known laws and the laws not yet discovered. The visible universe seems sturdy now. Galaxies turn slowly through space. Stars burn for millions or billions of years. Planets cool, oceans gather, chemistry grows intricate, and life begins to make use of matter, as though it had always been waiting for the opportunity. But the deeper story is far less secure than it looks. All of this appears to depend on a tiny asymmetry in the earliest moments of cosmic history, a slight excess of matter over antimatter that survived when almost everything else was annihilated away. That is what makes the subject so extraordinary. The universe did not need a large advantage. It may have needed only about one extra matter particle for every billion matter and antimatter pairs. From that almost vanishing residue came atoms, then gas clouds, then stars, then heavier elements, then planets, then the long chemical chain that made biology possible. The material world was not guaranteed. It seems to have emerged from a very small imbalance with very large consequences. The scientific path toward that realization has been one of the great achievements of modern physics. Paul Dirac's theory pointed toward antimatter before it was observed. Carl Anderson found the positron in cosmic rays. James Cronin and Val Fitch showed that charge parity symmetry could be violated. Andrei Sakharov identified the conditions needed for a cosmic matter excess to form. Since then, particle physics and cosmology have worked together in a remarkably close partnership. Accelerator experiments, neutrino observatories, antimatter traps, gamma-ray telescopes, and measurements of the cosmic microwave background have all contributed pieces to the same story. And yet the central answer remains incomplete. The standard model of particle physics explains an enormous amount, but the charge parity violation it contains does not seem sufficient to account for the full matter excess observed in the universe. That is why the search continues. Experiments at CERN, Fermilab, Keck, and other laboratories keep testing the limits of known physics. Cosmological observations keep tightening the conditions any successful theory must satisfy. New ideas involving neutrinos, extended Higgs sectors, grand unified theories, supersymmetry, and baryogenesis models remain under study because the universe still appears to be hinting at something deeper. So the cosmic imbalance remains one of the most profound mysteries in modern science. It is a reminder that the existence of everything solid, luminous, and alive may depend on a slight imperfection in the laws of nature. The stars overhead, the atoms in the body, and the history of matter itself all seem to trace back to one delicate fact. The universe, in all its scale and beauty, may exist because fundamental physics was not perfectly balanced.